Hello there and welcome to Science for Sleep, where curiosity settles in beside you and the biggest questions in the universe take on a gentler, quieter shape. I'm glad you're here, finding a moment to unwind, let the day fall away, and wander with me through something vast without needing to stay fully awake for every detail. Tonight, we're drifting toward a place that sounds dramatic, almost like it belongs in a movie rather than in astronomy. It's an idea that sits right at the border between science and imagination, the kind of idea that seems too big to fit inside a single thought, yet somehow invites you in anyway. We're exploring what actually happens at the edge of the universe. It's an interesting phrase because the word edge makes you think of cliffs, fences, or boundaries painted with bright lines. But when you bind that word to the universe, everything becomes less straightforward. The universe isn't a box, and it's not a sphere hanging in space with a hard limit that you can bump into if you're not careful. Yet the question keeps appearing because humans naturally want to know where things start, where they stop, and whether there's a final point where the familiar gives way to something else. The edge of the universe feels like a place where you could stand, look out, and see everything fade into something unknown. Not in a dramatic or frightening way, but in the ordinary sense of wanting to understand what's just beyond the horizon. Before we settle in and start teasing apart what this edge means, I'd like to know something simple about you, wherever you are right now. Where are you listening from tonight? Maybe you're stretched out in bed, maybe resting on a couch, or maybe you found a quiet spot to sit for a few minutes. What time is it where you are? It's always interesting to think about how many locations and moments meet right here, in this small corner of calm. Some people are listening in the middle of a slow evening. Others are starting their morning and letting this carry them into a gentler rhythm than usual. Some might already be half asleep, letting the words drift across their thoughts like a soft background hum. And if you find this space helpful, if the pace makes the day unwind or the explanations give you something interesting to think about while you get comfortable, I'd be grateful if you gave the video a like or subscribed. It helps this little sleepy corner reach the people who might need something quiet and steady, especially on nights when their thoughts don't want to settle down. But there's no pressure at all. This is about taking things slowly, letting ideas settle in without urgency, and giving your mind a chance to rest. Now, as we move gently into this topic, it helps to start by letting go of the idea of an edge, the way we normally use the word. When we talk about the edge of a table, a field, a forest, or even a city, there's a clear separation between the thing and what isn't the thing. One side is the object, and the other side is everything else. But the universe is different. It's not something floating inside a bigger space. There's no outer container, no surrounding void waiting just beyond reach. So when people ask what the edge of the universe is, they're not asking about a physical barrier. They're asking what lies at the limit of everything we can observe, everything we can measure, and everything we can meaningfully describe. The universe has a limit, but it isn't a wall, it's a distance. More precisely, it's a distance shaped by the speed of light and the amount of time the universe has existed. Light travels very quickly, but it doesn't have infinite time to reach us. The universe has only been around for about 13.8 billion years, which means there's a furthest edge of what's had time to send its light to us. That distance forms a kind of spherical boundary around us called the observable universe. It's large, far larger than the number 13.8 might suggest. Because space has expanded over time, the furthest places whose light can reach us are now much farther away than they were when that light began its journey. They sit roughly 46 billion light-years away, forming a kind of horizon that we can't see beyond. And that's where the first sense of the universe's edge appears, not as a barrier, not as a final border, but as a limit of visibility. It's similar to standing on a beach looking out at the ocean. The water doesn't end at the horizon, your vision does. The universe works in a similar way. What lies beyond the observable universe hasn't sent any information to us. Not because it's empty or separate, but simply because the light from that far away hasn't had time to arrive. The universe may extend much farther, perhaps infinitely. We just can't see it yet. Before we go farther, it's worth taking a slow breath and letting that idea settle. The edge of the universe isn't sharp. It isn't even fixed. It's a moving boundary shaped by time. The longer the universe exists, the more its light can travel, and the farther that boundary extends. It's a horizon that grows not because space is opening a door, but because the universe itself is giving us more time to see what's out there. And even as that boundary grows, the expansion of space can push distant regions away faster than light can cross the space between us, meaning that parts of the universe will always remain out of reach. This creates a gentle tension between what is knowable and what isn't. Not an urgent tension, more like the quiet awareness that the further we look, the more the universe pushes back with its own limits. Our instruments keep improving, our telescopes keep reaching deeper into the past, yet no matter how far we stretch our observations, the horizon continues to define what's accessible. It's not a wall, it's a boundary shaped by reality itself. Understanding this boundary will guide every step of our slow exploration tonight. We'll look at why the universe has a horizon, why the expansion of space affects what we can observe, how the light from distant galaxies tells us the story of the past, and what modern physics says about what lies beyond that horizon. The goal isn't to reach a final answer, because science doesn't have one yet. The goal is to understand the pieces we do have and let them settle into something you can picture without rushing. It's also worth acknowledging that when people imagine the edge of the universe, they often picture a physical place. Maybe a zone where stars thin out, or a curtain of darkness, or a region where the laws of physics become strange. In reality, nothing interesting happens at the edge of the observable universe from the perspective of the universe itself. The galaxies near that horizon aren't stretched thin or fading out. They're simply far away, moving with the expansion of space and sending us light that has been on the road for billions of years. They're normal places living normal cosmic lives. The only unusual thing about them is their distance from us. If we were standing on a planet 30 billion light-years away, our observable bubble would shift, revealing regions of space we can't see from here, and hiding others that we currently observe. Every location in the universe has its own horizon, like overlapping bubbles. There isn't one universal edge for everyone. There are many edges, each unique to its observer. The universe doesn't have a single boundary. It has countless vantage points, each with its own limit. As we continue onward, we'll take our time moving from one idea to the next. We don't need to rush. This is a topic that becomes clearer when approached slowly, letting each concept build naturally into the next, without trying to grab everything all at once. The universe is immense, but that doesn't mean understanding it has to feel overwhelming. We can walk through it step by step, letting each detail find its place. So let's drift a little deeper into the question of what it means for the universe to have limits. Not limits imposed by walls or borders, but limits defined by the way space expands and the way light travels. These limits shape everything we can observe, everything we can map, and everything we can describe. And once we understand how those limits form, the idea of the universe's edge begins to look much less like a physical frontier and much more like a natural consequence of how reality works. When people picture the universe, many imagine something with a clear outline, almost like an object you could sketch on a piece of paper. You might think of a sphere suspended in darkness, or a kind of giant bubble floating in some larger emptiness. That image feels intuitive because everything we interact with in daily life has boundaries. A room has walls, a park has a fence, a country has borders that you can look up on a map. Even concepts that don't have physical barriers still carry a sense of limits. A busy schedule has a beginning and an end. A road trip has a starting point and a destination. Human experience works nicely with clear edges, so it's natural to imagine that the universe must also follow that pattern. But when you look closely at how space behaves, the usual sense of boundaries becomes difficult to apply. A useful way to start is by imagining yourself in a very large room. Not a regular one with corners and windows, but an enormous open area that stretches far in every direction. If you walked in any direction long enough, you would eventually reach a wall, because even the biggest building has an outer surface. That's usually what we expect. But now imagine that the room doesn't have walls at all. You walk, and the space continues in front of you indefinitely. The floor stays level, the air stays the same. Nothing marks a transition from inside to outside. There is no sign that the room ends because the room doesn't end. It isn't contained in something else. It's simply the entirety of the space that exists. If you tried to reach the boundary, you'd never find one because the boundary doesn't exist as a physical feature. The universe behaves more like that second kind of room. It doesn't sit inside a bigger container. It isn't an object with an outside. There is nothing beyond the universe, not in the sense of a separate space that it occupies. The universe is all of space itself. When someone asks where the universe is located, the question doesn't really fit because location only makes sense within space. Asking what's outside the universe is like asking what's north of the North Pole. It sounds meaningful at first, but when you try to answer it, the question unravels. North is a direction defined on Earth's surface. Once you've reached the northernmost point, there is no farther north to go. Similarly, once you've reached the boundary of space, there is no space beyond it in which to travel. The idea of location outside the universe loses meaning, because space isn't something the universe is inside. Space is part of the universe itself. That's part of why physicists say the universe has no physical edge. But that doesn't make the universe simple to picture. The mind wants to anchor things. It wants to hold on to an image, even if the image is only a tool rather than a perfect representation. One way to help the idea settle is to imagine walking across the surface of Earth. If you walk east long enough, you eventually return to your starting point without falling off the planet. You never encounter an edge, yet the surface doesn't go on forever in a straight line. It wraps around itself. The surface is finite but unbounded. You can travel endlessly without hitting a wall. However, the universe is not known to wrap like Earth's surface, and the analogy stops there. The comparison isn't about the exact shape, but about the concept of something that has no edges even if it has structure. In the case of the universe, the shape could be finite or infinite. Both options are possible, and either one avoids the need for a boundary. A finite universe with no edge might curve back on itself in higher dimensions, meaning that if you travelled far enough in one direction, you could return to where you started, not because the universe loops like a racetrack, but because the geometry of space allows closed paths. An infinite universe simply extends forever without wrapping. The important thing is that neither possibility includes a wall you can hit. The universe doesn't need a surrounding void. It doesn't need a border separating the inside from an outside. The universe is all there is. Its size and shape are open questions, but its lack of a physical edge is a common conclusion across many models. To understand why edges don't appear naturally in cosmology, it helps to look at how space expands. Expansion isn't like stretching a balloon from the outside. There is no external force pulling at the edges. Expansion happens everywhere at once. The distance between locations grows, not because space is swelling into another medium, but because the metric that defines distances changes over time. Picture dots on the surface of a balloon that's being inflated. The dots move apart even though they aren't moving across the surface. The surface itself is stretching. Now remove the balloon and imagine the stretching happening without any surrounding air or any external hands pulling. That's closer to how cosmic expansion works. There is no need for an outer region for space to expand into. Space expands internally. Every region grows relative to every other region. This leads to another question many people have when thinking about edges. If the universe began with the Big Bang, doesn't that imply an explosion from a point into surrounding emptiness? It would be reasonable to imagine a central origin and a blast radiating outward. But the Big Bang wasn't an explosion in space, it was the expansion of space. Every region of space was once extremely hot and dense. The expansion didn't begin at one location. It began everywhere at once. There is no center to the expansion, just as there is no edge. Every point in space sees the universe expanding away from it, because expansion is a property of space itself, not a motion of objects through space. If you were in another galaxy, you would see other galaxies receding in the same way we see them receding from us. No matter where you stand, space stretches uniformly. This uniformity removes the need for a boundary. There is no region that isn't part of the expansion. There is no empty exterior waiting for the universe to reach it. When you understand expansion as something that happens to all of space, the idea of an outer limit becomes unnecessary. The universe doesn't grow into something. It grows within itself. Still, if the universe can be boundless, what exactly does it mean when astronomers say we can observe only a limited portion of it? This question often leads people to imagine that the observable region is a kind of enclosed bubble, and that outside the bubble lies the rest of the universe separated by a border. But in reality, the observable region is shaped by the finite age of the universe and the finite speed of light. There are regions too far away for their light to have reached us since the beginning of cosmic history. They aren't blocked by anything. The light simply hasn't had time to arrive. These distant regions are not hidden behind a wall, but behind time itself. If we wait long enough, some of that light will reach us. Other regions, however, are moving away faster than light can travel due to the expansion of space, so their light will never reach us. This creates a horizon defined by the relationship between expansion and light speed. The horizon isn't an edge of the universe, it's an edge of visibility. If you were in a different galaxy, your horizon would be centered there, not here, meaning the universe has no single shared boundary. Each place in the universe has its own horizon, shaped by the history of light and the history of expansion. This perspective highlights how misleading the word edge can be. It makes it sound like there should be something physically present that marks a transition. But the universe doesn't behave like that. Its limits are observational, not physical. They exist because of how time and light work, not because of an outer surface. Many people still want to imagine what would happen if you somehow travel toward what they think of as the edge. Would you reach a region that becomes thinner, with fewer stars and galaxies? Would you encounter a sudden fall-off where space ends abruptly? In reality, nothing changes as you travel outward. If you could freely move through space without being limited by distance or time, you would keep encountering galaxies, clusters, and stretches of cosmic emptiness scattered across great distances. You wouldn't notice any thinning caused by approaching an outer boundary. The distribution you see continues as far as current models can predict. There is no sign that galaxies cluster toward the center or fade near an edge. Observations show uniform structure on the larger scales. This uniformity is part of the basis for believing in a universe without edges. If there were a physical boundary, you would expect distortions. You would expect densities to change as you neared a limit. We don't see that. If you consider an infinite universe, the idea of edges becomes even more unnecessary. Infinite space has no end by definition. But even finite space avoids edges by curving or connecting in a way that removes boundaries. Some models describe space as analogous to the surface of a sphere, except in higher dimensions. You can travel endlessly without reaching a border even though the total size is finite. This is a possibility consistent with Einstein's equations, although the exact geometry of our universe is still being refined using observations. Another complication in thinking about edges comes from the fact that space can have curvature. Curvature affects how lines behave. In flat space, parallel lines remain parallel. In curved space, those lines might converge or diverge even if they never curve in the traditional sense. Curvature doesn't create a wall, but it changes how distance and direction work. If the universe has positive curvature, travelling in a straight line long enough could eventually bring you back to your starting point. If it has zero or negative curvature, you could travel forever without looping. In none of these cases does a physical edge appear. It's also worth noting that when cosmologists map the universe, they don't picture a large sphere with stars sprinkled around it and empty space outside. They picture a grid of expanding space-time. That grid has no border because space-time itself is the thing being described. There is no outside. The map represents all of reality. When you accept that space isn't inside anything, the need to imagine walls disappears. Even with all this, the human mind still circles back to the question: if there is no boundary, what stops the universe? What keeps space from just continuing forever? But that question assumes that space needs something external to limit it. Space is self-contained. It doesn't need to be prevented from expanding beyond a boundary. It doesn't need a container. It simply is what it is. If it's finite, its shape closes on itself. If it's infinite, it continues without end. In both cases, the absence of a boundary is completely natural. Understanding this may not feel intuitive at first, especially because so much of daily life involves containers, surfaces, and edges. A cup holds water, a house has walls, a book has a cover. But the universe is not an object in the way those things are. It's the framework in which all objects exist. Trying to place the universe inside something else doesn't work because the concept of something else only makes sense within space. You can't put space inside space. The universe is the totality of space-time, matter and energy. There is nothing outside it because outside is a spatial idea. So when we talk about the universe as a boundless room, we're not saying that it's a literal room or that it has walls removed. We're describing a space that doesn't rely on an outer shell. The room is boundless because it doesn't end at a physical boundary. If you travelled through it, you'd never reach a place where the universe stops and something outside begins. There is no outside. There is only more universe. And as we move forward, the idea of a boundless universe will become important. Many of the questions about edges become easier to explore once you understand that an edge, in the traditional sense, doesn't exist. The universe has limits in what we can observe. It has limits in what light can show us. It has limits shaped by expansion and time. But those limits are not the same as borders. They don't mark the end of space, they mark the end of visibility. The phrase, "how far we can see into the universe," sounds like something simple, almost like looking across a very big field or standing on a mountain and viewing a distant horizon. But when you think about what it means to see in a cosmic sense, the picture becomes far more intricate. Seeing isn't just about light arriving at your eyes. It's about how light travels, where it comes from, how long it takes to reach you, and what happens to space itself during that journey. The universe doesn't offer a clean, sharp edge where your vision stops because something blocks it. Instead, the limits on how far we can see are shaped by the history of space, the behavior of light, and the expansion that continuously stretches distances over billions of years. When you look at the night sky, the light from a nearby star may have travelled only a few dozen years to reach you. The light from a distant galaxy might have spent millions of years on the road. And the light from the most ancient regions of the universe has been travelling for nearly the entire history of the cosmos. Everything you see in the sky represents a different moment in time. This isn't poetic. It's just how light works. Light doesn't arrive instantly. It moves at a constant speed, and that speed sets a natural limit on what regions of the universe can send you information. You can only see the places whose light has had enough time to reach you since the moment the universe began producing light. This forms a horizon. It's not a physical barrier. It's a distance that light hasn't crossed yet. The idea of a horizon in cosmology is similar to standing near the ocean and watching the water meet the sky. The horizon you see on the beach isn't the edge of the ocean. It's just the farthest point your eyes can detect due to the curvature of Earth. If you had a boat or a plane, you could see farther, and if you moved to a different location, the horizon would shift with you. In the universe, the horizon also shifts depending on where you stand, except the shift isn't caused by physical height or perspective. It's caused by time and the speed of light. Each observer in the universe has their own horizon centered around their own location. There is no single shared boundary. The universe appears different depending on where you sit, not because the universe changes, but because your horizon changes. Astronomers often talk about the observable universe to describe the region of space from which light has had enough time to reach us. That region is vast. Even though the universe is 13.8 billion years old, the observable radius is about 46 billion light-years. This number surprises many people because it's larger than the age of the universe multiplied by the speed of light. The explanation lies in the expansion of space. While the light was on its way, space continued to stretch, increasing the distance between us and the region that emitted the light. By the time the light arrives, that region is much farther away than the distance the light travelled. So the boundary of what we can observe isn't limited to 13.8 billion light-years. It reaches much farther because space itself has been expanding during the entire journey. This expanding horizon is the first boundary that shapes what we can see. It marks the furthest distance from which light has had enough time to reach us. But understanding this horizon means understanding that it isn't fixed. As more time passes, the horizon expands. The light that has been travelling across space continuously reveals new regions. It's as if the universe slowly unveils itself at a measured pace, not because it's holding back, but because information takes time to arrive. If you could fast forward billions of years, you would see more of the universe, at least up to the point where expansion outpaces light's ability to bridge the gap. This brings us to the second boundary that affects how far we can see. While light has a constant speed, space can expand faster than that speed. This doesn't violate physics because expansion isn't an object moving through space. It's the stretching of space itself. When distant galaxies are carried away by expansion, the space between us and them grows. If that expansion rate increases enough, the light they send may never reach us, because the distance grows faster than the light can close it. This creates a second kind of horizon called the cosmological event horizon. It's the boundary that divides regions of space whose signals will eventually reach us from regions whose signals will always remain out of reach, no matter how long we wait. If you imagine the universe as a series of concentric shells centered around your location, the first shell marks the limit of what we have seen so far. The second shell represents the limit of what we can ever see. Between these two shells lies a region of space that has already been observed, but might eventually drift out of reach if expansion accelerates. In such cases, the last light we receive from those regions will mark the end of their visibility. After that point, they fade from our observational universe, not because they disappear, but because expansion prevents any further communication. The existence of an event horizon can make the universe feel more mysterious. There may be countless galaxies, clusters, and structures that will forever remain invisible to us. They exist, but we will never receive their light. The idea that parts of the universe can become unreachable, even after billions of years of light travel, adds a layer of complexity to the question of boundaries. These boundaries are not walls placed around the universe. They're thresholds created by the relationship between expansion and the speed of light. They highlight the fact that our picture of the cosmos is shaped by physical rules rather than geometric shapes. When we look deeper, we find that the horizon isn't just a single number. It changes depending on what kind of light we're observing. Optical telescopes capture visible light. Radio telescopes capture wavelengths that travel differently through space. Some instruments detect microwaves, capturing the oldest light in existence. Each type of observation offers a different view, and each reveals its own limit. For example, visible light lets us look back billions of years, but it's eventually blocked by the fog of the early universe, a period when space was filled with charged particles that scattered light. Before that time, light couldn't travel freely. The universe was opaque, and optical observations can't see past that point. The first light that could travel freely through the universe came from a time called recombination, roughly 380,000 years after the Big Bang. Before that moment, electrons and protons existed in a plasma state. Photons collided constantly with these particles, unable to propagate long distances. Once the universe cooled enough for electrons to combine with nuclei to form neutral atoms, space became transparent. Light from that era has been travelling ever since, stretched into microwaves by the expansion of space. This light forms what we call the cosmic microwave background. It's the oldest direct signal we can detect. No matter how advanced our telescopes become, we cannot look back beyond that point using light. The nature of the early universe prevents it. This creates another type of horizon, one based on the physics of the early universe rather than distance. Even if we could travel faster than light or see across expanding regions, the opaque state of the early cosmos still prevents us from seeing the very beginning. We can infer what happened earlier through mathematical models and observations of later behaviour, but we can't directly view it. This opacity acts like a veil drawn across the earliest moments. Not a solid barrier, but an observational limitation that no amount of technology can erase. So the question of how far we can actually see has multiple answers. We can describe the radius of the observable universe. We can describe the horizon created by expansion. We can describe the limit imposed by the opaque early universe. Each boundary interacts with the others, shaping our view of the cosmos like overlapping layers. When you combine them, you get a complete picture of why the universe seems to have a limit, even though space itself has no edge. These horizons have consequences for how we understand cosmic structure. When we map galaxies, we're not just mapping distance, we're mapping time. A galaxy billions of light years away appears not as it is now, but as it was billions of years ago. If we look far enough, we see galaxies in their early stages, smaller, clumpier and more chaotic. We see stars forming at rapid rates. We see gas clouds collapsing. The deep image we construct isn't a snapshot of the universe in the present. It's a layered history. The horizon becomes not just a boundary of visibility, but a boundary of time. The farther we look, the earlier the universe becomes. At the limit, we reach the cosmic microwave background, a uniform glow that marks the earliest visible era. This observation changes how we think about the universe. If all you saw were stars and galaxies at their current stage of evolution, you might imagine the universe has always looked like it does now. But the horizon shows that the universe had a beginning, that it evolved, and that its structure changed. It shows that galaxies formed gradually, and that cosmic history is written in the light we receive. Without horizons, we wouldn't have access to this timeline. The universe would be a static picture. Instead, we observe its story in layers. These layers reveal another property of horizons. They remind us that looking into the distance is always a look into the past. Every bit of light you see is telling you about a moment long gone. When you look at a star 50 light years away, you're seeing it as it was 50 years ago. When you look at a galaxy 10 billion light years away, you're seeing it when the universe was still young. This temporal layering is inseparable from distance. Horizons exist because time and space are linked. The universe has a finite age, and that age shapes what we can see. If you could remove the horizon and observe the entire universe at once, you wouldn't see a single moment. You would see different regions at different ages. This is why cosmology relies on careful interpretation. The limits of visibility aren't just about distance. They're about how light carries information and how expansion stretches that information. The horizon is defined by the interplay of three things: the speed of light, the age of the universe, and the expansion of space. These factors create natural constraints that carve out the observable region. Within that region, observations grow more difficult as distance increases. Light becomes redshifted, stretched to longer wavelengths by expansion. Galaxies become faint, their details blur. Eventually their light stretches into wavelengths our instruments struggle to detect. Even before reaching the limit of what we can ever see, practical observational limits appear. Telescopes must detect faint signals buried in noise. They must separate tiny sources from the background. They must correct for distortions caused by dust, gas, and gravitational lensing. The horizon isn't a clean line where vision stops. It's a gradual decline in clarity as distance increases. As technology improves, some of these limits shift. Telescopes see farther, instruments detect fainter light, methods sharpen. But no matter how advanced our tools become, the fundamental horizons remain. We cannot see beyond the speed of light limit. We cannot receive signals from regions moving away faster than light. We cannot view the universe before it became transparent. These limitations define the boundary of the observable universe. They don't define the boundary of the universe itself. This distinction is important because it shapes our understanding of what lies beyond. The observable universe is not the full universe. It's only the region from which information has reached us. Beyond that region, space continues. There may be galaxies, clusters, voids, and structures that mirror what we see close to us. There may also be features we cannot imagine. The absence of visibility doesn't imply absence of content. It just means light hasn't bridged the gap. This perspective often brings people back to the notion of an edge. If we can only see part of the universe, doesn't that mean the observable region behaves like a kind of temporary boundary? In a way, yes, but only from our viewpoint. If someone lived 40 billion light years from here, their observable region would be different. The structure of their visible universe would overlap with ours, but not match it exactly. Their horizon would include regions we can't see and exclude regions we can. The universe offers each observer a personal bubble of visibility shaped by light and time. These bubbles overlap across space, forming a mosaic of horizons. There is no single shared border. The universe is not limited by our view. Our view is limited by physical rules. When you think about distance, you probably imagine something simple. A gap between 2 points, a stretch of road, the space between 2 buildings, the time it takes to walk from one place to another. Distance feels like a straightforward measurement. You can mark it with a number, tie it to a physical path, and treat it as an amount of space that separates one location from another. But when we move from everyday life to the scale of the universe, distance behaves differently. It's still a measure of space, but it becomes tightly linked to something else. It becomes tied to time itself. This shift happens because the universe is vast and because light, which carries almost all of the information we use to understand the cosmos, travels at a finite speed. If light could move infinitely fast, you would see everything in the universe as it is right now. Every galaxy, every star, every cloud of gas would be visible in its current state. There would be no delay. But because light travels at a constant speed, roughly 792 kilometers per second, the farther away something is, the longer its light takes to reach you. That means when you look at something far from Earth, you're not seeing it as it exists today. You're seeing it as it was at the moment the light left it. Distance turns into time. When you look at the moon, the light reaching your eyes left it about a second ago. The sun's light takes roughly 8 minutes to get here. The nearest star sends light that takes over 4 years to travel. A galaxy millions of light years away appears as it was millions of years ago. Every step outward reveals an earlier moment in cosmic history. The night sky becomes a timeline layered across distance. The farther you look, the older the scene becomes. This isn't a poetic idea, it's simply the way light works. This connection changes how we understand the universe, because the cosmic landscape isn't just a spatial map, it's also a historical record. Observations reveal different phases of the universe's development. Nearby galaxies show their present form. Distant galaxies reveal their younger selves. Very distant galaxies show the early universe still assembling its structures. The cosmic microwave background shows the universe as it was about 380,000 years after the Big Bang, long before stars or galaxies formed. The limit of what we can see becomes a limit of how far back in time we can look. The idea that distance equals time isn't just a curiosity. It forms the basis for how cosmologists reconstruct the story of the universe. If you collected all the observable objects and arranged them by distance, you would form a sequence of events that stretches from the near present to the earliest visible era. Each point would give you a snapshot of a different age. By comparing them, you could build a rough timeline. This layered view is what makes astronomy different from fields that study objects directly. You can't visit distant galaxies or rewind the universe, but you can observe the light arriving from various distances and reconstruct what happened. This approach introduces an unusual challenge. When you look farther into space, you aren't just looking at greater distances, you're looking at earlier periods. That means the universe looks different depending on how far away something is. Loose, irregular galaxies appear at vast distances because they formed when the universe was young. More structured galaxies appear closer because billions of years have shaped them. This creates a patchwork sky where different regions represent different moments. The cosmos is not a frozen snapshot. It's a series of moments captured across space. This arrangement is why astronomers can't simply map the universe as if it were a static grid. They have to consider how cosmic structures evolve. They have to account for the fact that distant objects haven't had as much time to develop. They have to understand how the expansion of space stretches light, shifts colours, dims objects, and affects measurements. When you look outward, you're always merging distance with time. There's no way to separate them. This connection becomes even more important when distances become extremely large. As you look billions of light years away, the universe becomes younger and more compressed. Structure hasn't fully formed. Galaxies appear small and chaotic, stars are hot and bright, gas clouds are denser, radiation is stronger. The deeper you look, the more the conditions change. Eventually you reach a point where the universe becomes too young for certain features to exist. There are no heavy elements, there are no complex structures, there are no planets. The universe hasn't had time to build them. If you look still farther, you reach a point where even galaxies haven't formed. You see early clumps of matter falling together under gravity. If you go farther still, you reach the cosmic microwave background, the earliest light we can detect. Beyond that point, the universe was opaque, filled with charged particles that scattered photons. You can't see through that fog directly. Light cannot show you anything earlier. The universe has a limit defined not by distance in the usual sense, but by the relationship between distance and time. Beyond that limit, you cannot observe because no light from that era has ever reached your eyes. That opaque boundary marks a turning point in cosmic understanding. It tells us that the universe had a beginning. Not a beginning in the sense of a sharp edge, but a beginning in the sense of a hot, dense state, evolving into something more structured. It tells us that time has a direction. It tells us that the universe has a history written in the light we receive. But most importantly, it tells us that the universe itself is not accessible as a single moment. Every observation is a look into the past, and the deepest observations are the oldest. This might make the universe sound easier to understand, but the cosmic light limit brings complications. If distance equals time, you need to know how distance should be measured. In everyday life, distance is straightforward. You take a ruler or a tape measure. You define a straight path. You measure the length. But in the universe, there is no single distance. Because space expands, there are multiple ways to define how far away something is. You could measure the distance the light travelled. You could measure how far away the object is right now. You could measure the distance as it was when the light started its journey. You could measure the distance as it would be without expansion. Each method gives a different number because the universe isn't static. This creates confusion when comparing cosmic distances. When astronomers say something is 13 billion light-years away in terms of look-back time, they mean the light took 13 billion years to reach us. But the object itself is now much farther away because space expanded while the light travelled. That object might currently be over 30 billion light-years away. If you used another measure, you might get a different number again. None of these measurements are wrong. They just describe different aspects of the same situation. Distance becomes complex because time and space shift together. This complexity affects how we understand what lies at the cosmic boundary. When the universe was young, distant regions were much closer. Their light had an easier time travelling. As expansion accelerated, distances grew faster than light could keep up. Regions that were once visible drifted out of reach. You might think of this as a dynamic horizon. It shifts, expands, and sometimes hides regions that used to be within sight. This movement shows why distance is not a simple quantity. It changes as the universe changes. To understand this clearly, you might picture a line of points moving apart. If you mark one point as your location, the points farther away move faster due to expansion. Eventually, some move away at speeds light cannot overcome. Their signals will never reach you. Even though nothing is travelling faster than light through space, the expansion of space itself stretches the distance. This creates a permanent limit. Parts of the universe become unreachable, not because they disappear, but because their light cannot cover the growing distance. This leads to a subtle realization. The cosmic light limit is not only about how far light has travelled, it's also about whether light can continue to reach us. Some regions of the universe are visible today but eventually won't be. We're receiving their final photons. After a certain point, no new light will arrive from them. They will fade into darkness from our perspective. They'll still exist. We just won't be able to see them. This future limit shows how time shapes distance and visibility. When we observe distant galaxies, we aren't seeing a fixed reality. We are seeing a combination of distance travelled, time passed, and expansion effects. Light stretches into longer wavelengths. Infrared becomes microwave. Microwaves become radio. The farther the light travels, the more stretched it becomes. This process, called redshift, is one of the strongest indicators of how the universe expands. As expansion increases the distance the light travels, the wavelength grows, creating a clear signature of how the universe has changed. This stretching tells astronomers how long the light has been travelling. It also helps measure the rate of expansion. The higher the redshift, the older the light. The older the light, the farther away the source was when the light started its journey. But because expansion continues, the source is now much farther than that starting distance. This adds extra layers to how distance becomes time. It isn't just about how long the light travelled, it's about how much the universe grew while it travelled. This relationship explains why some objects appear faint or hard to detect. Their light stretches into wavelengths that are difficult to measure. It also explains why early galaxies look different. Their light was emitted at a time when the universe had fewer heavy elements, fewer large structures, and more energy in the background. The light we receive tells us about a universe that no longer exists in that form. Distance becomes a bridge to previous states. That bridge creates a unique window for science. Observing distant galaxies lets astronomers see how galaxies evolve. Observing clusters at different distances reveals how matter gathers. Observing the cosmic microwave background reveals conditions before structure formed. Without the cosmic light limit, these insights would be impossible. Instead, the limit becomes a tool. It allows researchers to reconstruct the timeline of the cosmos. The link between distance and time also changes how we imagine the universe as a whole. We cannot see the universe as it is moment by moment. We can only see it as it was. If you gathered all the light reaching Earth in a single moment, you would not get a picture of the universe today. You would get a collection of images from different eras. To understand the present universe, you must account for how old each signal is, how much space expanded, and how the object should appear now based on models of cosmic evolution. The actual present-day universe exists beyond what we can observe directly. This means that the cosmic light limit doesn't only shape what we see, it shapes what we can understand. It creates a barrier that separates direct observation from inference. Scientists build models to predict what the universe looks like beyond the light limit, using physical laws, simulations, and indirect evidence, but the boundary remains. The earliest moments are invisible. The current state of distant regions is invisible. The details beyond our light horizon remain hidden. Distance becomes time, and time becomes a filter. Even though this boundary is firm, it doesn't limit curiosity. Instead, it gives structure to exploration. It encourages questions about the early universe, about what happened in the opaque era, about how matter emerged from initial conditions, and about how space evolved. It encourages research on inflation, dark energy, and quantum fluctuations. The cosmic light limit points toward the earliest traceable events and invites scientists to fill in the missing steps. When you picture something expanding, you probably imagine an object getting larger inside a surrounding space. A balloon inflates into the air around it. Dough rises inside a bowl. Ripples in a pond spread across the water. These are examples of expansion, where something grows inside something else. There's always a container, an outside region, or a medium that the expanding thing uses to change its size. That's how expansion behaves in daily life, so it makes sense that when people hear that the universe is expanding, they imagine it stretching outward into some larger emptiness. They imagine edges moving outward, borders widening, or space pushing into a pre-existing void. But that picture doesn't fit what the universe actually does. When cosmologists talk about expansion, they don't mean the universe is growing into anything. There is no external space waiting to be filled. There is no margin the universe is spreading into. Expansion is something that happens within the universe itself. It's the stretching of space from within, not the motion of space into an outside region. Every part of the universe increases in separation from every other part, not because galaxies are flying through space like debris flung from an explosion, but because the distances between points of space grow naturally over time. Expansion is built into the structure of the cosmos. To understand this, it helps to think about how scientists detected expansion in the first place. In the early 20th century, astronomers observed that distant galaxies had their light shifted toward the red end of the spectrum. This redshift indicated that the galaxies were moving away from us. At first glance, it might seem like we're at the center of the universe and everything is flying outward. But as more galaxies were studied, it became clear that the amount of redshift was proportional to distance. The farther away a galaxy was, the faster it seemed to recede. This pattern didn't match an explosion from a single point. Instead, it matched something else. It matched a uniform stretching of space. Imagine dots drawn on a rubber sheet. If you stretch the sheet evenly, every dot moves away from every other dot. The dots farther apart move away faster because there's more rubber between them to stretch. None of the dots has a special role. None of them sits at the center. The movement comes from the sheet itself. That's similar to how the universe behaves. The galaxies aren't racing outward from a central explosion. They're carried by the expansion of space itself. This idea sounds unusual because nothing in everyday life behaves this way. But in cosmology, expansion isn't just a descriptive term. It comes from Einstein's equations of general relativity, which describe how space, time, matter, and energy interact. These equations allow the fabric of space to evolve over time. They allow distances to change. They predict that if the universe has certain properties, expansion is a natural outcome. The galaxies move apart not because they are pushed, but because the geometry of space changes. If you imagine the universe as a grid, with galaxies sitting on the intersections, expansion doesn't move the galaxies across the grid, it stretches the grid. The galaxies remain in place on the grid lines, but the spacing between them grows. The grid has no edges, it's not placed on anything, it's the entire spatial framework. Expansion simply multiplies the distances. This explains why galaxies appear to recede from all directions. No matter where you stand, you see expansion the same way. Every direction appears to stretch away from you, not because you're special, but because expansion works everywhere. Many people ask why the universe expands at all. If nothing is pushing it outward, what sets the expansion in motion? To answer that, you need to think about how the universe began. In the earliest moments after the Big Bang, the universe was extremely hot, dense, and energetic. Expansion wasn't an explosion, but a rapid growth of space. The energy contained in that dense state created a kind of internal pressure. Once expansion began, the universe kept growing because nothing stopped it. Space doesn't require an outside region to grow into. It simply expands because the physical laws permit it, and because nothing counteracts that expansion on the larger scales. Gravity could have slowed or reversed the expansion if the universe had contained enough matter and energy. If the density had been significantly higher, gravity might have pulled everything together, causing the universe to contract. But observations showed that the universe's density wasn't high enough to halt expansion. Instead, expansion continued. In fact, not only did it continue, but billions of years later, something unexpected happened. The expansion began to speed up. Astronomers discovered this acceleration in the late 1990s, and it led to the concept of dark energy, a form of energy that seems to be built into space and causes expansion to accelerate. This acceleration means that expansion isn't fading. It's not slowing toward a halt, it's speeding up. Regions of the universe are drifting apart faster and faster over time. This increase creates another reason the universe cannot have a traditional edge. If expansion accelerates everywhere, no special boundary can form where expansion suddenly stops. There is no wall that marks the end of space. Every part of the universe participates in expansion. This uniformity eliminates the idea of a fringe where space thins out. Expansion is not like stretching a balloon where the rubber has a physical limit. The universe's expansion doesn't rely on material substance stretching over an outside surface. It is the geometry of space growing. This difference matters. When you stretch a balloon, you can talk about the outside of the balloon. You can talk about the air it expands into. But the universe doesn't work that way. Space doesn't sit inside another space. There is no external volume waiting to be filled. The universe is all of space, so expansion doesn't require anything beyond itself. That's why cosmologists say the universe is not expanding into anything. It's not inflating into a void or filling an empty background. Expansion is simply the increase of distances within the universe. To make this clearer, you can think of a simpler analogy. Picture a grid of lines on a sheet of paper. If the sheet is pulled in all directions, every intersection moves relative to the others. But now imagine the sheet represents the entire three-dimensional universe. It doesn't sit in a larger four-dimensional space. It is the entire spatial extent. The stretching happens internally. There is no beyond. This internal expansion leads to another question people often ask. If the universe is expanding everywhere, does that mean galaxies are growing? Do planets expand? Do atoms stretch? The answer is no. Expansion acts on the large scale, on distances between galaxies and clusters of galaxies. It doesn't act on objects that are held together by forces stronger than the gentle pull of cosmic expansion. Gravity holds galaxies together. Electromagnetic forces hold atoms together. The expansion of the universe is too weak to overcome these forces on small scales. So your body doesn't expand. The solar system doesn't expand. The Milky Way doesn't expand. Only the space between large cosmic structures stretches. This selective effect is part of why expansion is so difficult to visualize. It acts everywhere but only becomes noticeable across enormous distances. The behavior of expansion becomes even more interesting when you consider what happens to light traveling through expanding space. The stretching of space also stretches light. A photon that begins with a certain wavelength gradually gets stretched as it moves across the expanding universe. Its wavelength increases, shifting from visible to infrared, from infrared to microwave, and from microwave to radio waves. This stretching contributes to the redshift we observe in distant galaxies. The farther the light travels, the more it is stretched. This effect provides strong evidence for expansion. Without expansion, this stretching wouldn't occur. Redshift also explains why extremely distant objects become difficult to see. Their light stretches so much that it moves beyond the range of normal detection. Even with advanced telescopes, the signal weakens as the wavelength grows. This is part of why distant galaxies appear faint. They aren't all small or dim, many are bright. But the stretching of light reduces their brightness and shifts their emission into wavelengths harder to detect. Another important aspect of expansion is the discovery that space can expand faster than the speed of light. At first, this sounds impossible, because nothing is supposed to travel faster than light. But the rule applies to objects moving through space, not to space itself. The expansion of space isn't limited by the speed of light. If two galaxies are far enough apart, the expansion between them can cause them to move away from each other faster than light can bridge the gap. This doesn't break physical laws because the galaxies themselves aren't speeding through space. The space between them is growing. This effect creates an event horizon, a limit to what we can ever observe. Some regions of the universe are moving away so quickly that their light will never reach us. This is another reason the universe has no edge. There is no boundary we can approach. Instead, there are regions forever beyond our reach, not because the universe ends, but because expansion outpaces communication. When you consider all of this, you can see that expansion creates boundaries without having edges. Expansion shapes what we can observe and what we can never access. It shapes the relationship between distance and time, the redshift of light, and the fate of galaxies. But these boundaries are not physical walls. They are consequences of the universe's structure. You might think about the idea of a shrinking observable region over time. As expansion accelerates, more and more galaxies drift beyond our communication horizon. They won't vanish instantly. Their light will continue to arrive until the last photons reach us. But eventually they will fade. They will move beyond the cosmic horizon. Even though they continue to exist, we won't see them. This gradual fading is not a sign of edges. It's a sign that expansion shapes what's visible. The growth of the universe also affects how we imagine its overall size. If space expands uniformly, any given region today was smaller in the past. That means the early universe was compact. Everything was closer, hotter, and denser. Over time, expansion thinned the density, cooled the temperature, and separated galaxies. The universe grew from a smaller state to a larger one, but this growth doesn't imply a boundary. If the universe was infinite at the beginning, it remained infinite. If it was finite but unbounded, it stayed finite but unbounded. Expansion changes size, but not topology. It scales distances without altering whether the universe has walls. Thinking about this scaling helps explain why expansion is sometimes compared to a stretching fabric. Not because the universe is literally a fabric, but because scaling distances create similar effects. If the universe doubled in size, every large distance would double. But nothing inside galaxies would stretch because gravity holds them together. Expansion acts only on the broad structure. The most surprising part about expansion is that it doesn't have a predetermined end. There's no physical law forcing it to stop. It might slow if dark energy changes. It might accelerate indefinitely. It might behave in ways we haven't yet understood. Observations show that expansion currently accelerates, and most models suggest it will continue to do so. But expansion doesn't create an outer limit. It doesn't produce a fringe, a border, or a front. It simply increases distances everywhere. The phrase observable universe can sound as if we're talking about a special zone carved out of something larger, almost as if our corner of the cosmos sits inside a bubble with a clear outline. But the idea of an observable universe isn't about a physical enclosure or a boundary placed around us. Instead, it describes the region of space from which light has had enough time to reach us since the universe began. It's a practical concept rather than a structural one. There is nothing separating the observable part from the rest. There is no shell or membrane holding us in. The observable universe is simply the portion we can see, shaped by the age of the universe, the speed of light, and the rate at which space expands. To understand why it forms a kind of bubble around us, imagine standing in the middle of a field on a foggy morning. The fog limits how far you can see. You aren't surrounded by a wall. You're surrounded by a distance beyond which visibility drops away. If you walk across the field, the visible region follows you, always centered on your position. Someone standing far from you sees a different set of trees, fences, or hills. Their visible region overlaps with yours, but it isn't identical. That's similar to how the observable universe behaves. It follows each observer. If you lived in another galaxy, your observable universe would be centered there. You would see regions we can't and miss regions we can. Nothing about this bubble is fixed in physical space. It doesn't privilege Earth or place us in a central position. It exists because of light and time, not geography. The universe doesn't surround us because we're important. It surrounds us because that's how light travels relative to where we are. Every observer anywhere in the universe has their own visible bubble just as large, centered on them. That alone shows that the observable universe is not the same as the actual universe. The actual universe is almost certainly much larger. It might even be infinite, but we can only see a portion of it because light hasn't had enough time to bring us information from the rest. There may be galaxies, clusters, and vast structures beyond our horizon that have existed for billions of years but remain unknown to us simply because their light hasn't arrived. The observable region defines what is accessible. It doesn't define what exists. If you imagine the observable universe as a spherical bubble around Earth, that sphere extends about 46 billion light-years in every direction. That distance results from adding two facts together. The universe is 13.8 billion years old, and space has expanded significantly over the time it took distant light to reach us. If space was static, the observable radius would be about 13.8 billion light-years. Instead, space has stretched, carrying distant regions farther away even while their ancient light travelled toward us. The result is a sphere much larger than what the age alone would suggest. Thinking of the observable universe as a bubble helps because it gives shape to what we can see. But unlike a metal ball or a soap bubble, this one has no material surface. You can't draw an outline around it in physical space. The boundary is defined by the limits of light, not by an object. If you could travel outward in any direction at immense speed, you wouldn't encounter a wall. You would simply pass into regions whose light has not yet reached Earth. You wouldn't notice a sudden change in the environment. You would see galaxies, clusters, and cosmic structures similar to those inside the observable region. The boundary is invisible because it's not a feature of space. It's a feature of our observational constraints. One of the most important consequences of living inside an observable bubble is that our picture of the universe is incomplete by design. Every map we make, every diagram we draw, and every model we build reflects only the region within this bubble. Anything outside it remains uncertain. Scientists can propose theories about what lies beyond, but they can't measure it directly. This isn't a technological limitation, it's a physical limit. No telescope or instrument can detect signals that have not had time to travel. Even in the future, this boundary will persist. Some parts of the universe are receding so rapidly due to expansion that their light will never reach us. This structure creates an interesting relationship between what is known and what is knowable. The observable universe contains the entire span of cosmic history, from the first light-producing era to the present day, all arranged by distance. But it doesn't contain the full universe. There is more beyond it. The size of that more could be modest or astronomical. It could extend for billions of light-years or stretch endlessly. The observable bubble is a sample rather than the whole. This sampling becomes especially important when scientists try to determine whether the universe is the same everywhere. One of the foundational assumptions in cosmology is that the universe is homogeneous and isotropic on large scales. Homogeneous means that matter is distributed uniformly when viewed from a wide enough perspective. Isotropic means that the universe looks the same in all directions. But these assumptions cannot be verified outside the observable bubble. They rely on the idea that what we see locally is representative of the whole. Observations so far support these assumptions. The cosmic microwave background appears uniform across the sky. Large-scale surveys show similar distributions of galaxies in every direction. But all of these measurements occur within our bubble. It's entirely possible that the larger universe has variations we can't detect. It may have different densities, different structures, or different behaviours beyond the horizon. It may contain regions where physical constants vary slightly. It may contain more matter in some areas and less in others. We only know that within our observable region, things appear uniform enough to support current models. It's a reasonable assumption that the rest is similar, but it remains an assumption. This incomplete visibility also affects how we think about cosmic structure. You can picture the observable universe as having layers. The closest layer contains stars and galaxies in their modern form. The next layer contains galaxies as they were billions of years ago. Farther out, you see the universe when it was young. At the boundary, you reach the cosmic microwave background, a faint glow that fills the entire sky. This glow represents the earliest visible era, when the universe first became transparent. Beyond that layer, the observable bubble ends, not because the universe stops, but because the light from earlier times cannot be detected. Some people imagine that the cosmic microwave background forms a kind of shell around us. It might sound like we're sitting at the centre of a giant sphere whose surface shows the early universe. But this interpretation isn't quite right. The cosmic microwave background doesn't surround us like the walls of a planetarium. It appears at a certain distance in every direction, because that's how far its light has travelled. If you stood in a distant galaxy, your cosmic microwave background would look exactly the same, centred on your position. Everyone in the universe sees the early universe surrounding them. It isn't a shell around Earth. It's the farthest visible light from every location. This reveals another important detail. The observable bubble isn't a fixed object in the universe. It depends entirely on where you are. Every point in space has its own bubble. These bubbles overlap extensively. If you moved 1 billion light years away, your observable universe would share many of the same galaxies we see now. But the arrangement would change. You might see regions currently beyond our horizon. Some of the distant objects we now observe would slip out of your view. The observable universe is personal to each observer, formed by the path that light takes to reach them. This personal nature means that the universe doesn't have a single observable boundary. It has countless overlapping ones. As a result, the true universe is larger than any single bubble. The size of the actual universe must be at least larger than our bubble by a huge factor. It could be exponentially larger. It could be infinite. The bubble is simply the part we can access. Thinking in these terms helps clarify why the observable universe is often described as a universe within a universe. What we see is complete enough to form a coherent picture, yet it is only a fraction of the whole. If you imagine the universe as a giant landscape, the observable bubble is the portion illuminated by a flashlight in a dark room. It gives you a local view. You can infer the shape of the rest from patterns, but you cannot see beyond the beam. This limitation doesn't reduce the value of what we observe. In fact, it makes the observable universe extremely meaningful. It contains all the evidence needed to reconstruct cosmic history, to understand fundamental physics, and to test theories of structure formation. It includes galaxies of all ages, clusters of various sizes, traces of early conditions, and signatures of the forces that shape the cosmos. It is rich in detail, full of clues, and large enough to study the universe's behaviour across immense scales. But it also holds mysteries. One of the most intriguing questions is how large the universe actually is. The observable bubble gives no clear answer. If the universe is infinite, our bubble is just one region of an endless expanse. If the universe is finite but unbounded, our bubble is still only a portion of a larger structure whose shape we can't see. If the universe has regions formed differently due to early fluctuations, we cannot detect them. The limits of light and time keep these questions open. Another mystery relates to how expansion affects the bubble over time. As expansion accelerates, distant galaxies move away faster. Light from some galaxies that we currently observe will no longer reach us in the future. Their final photons are on their way. After those last signals arrive, the galaxies will slowly fade from our view. Over very long timescales, the observable bubble will shrink in terms of what it includes, even as its radius increases. The sphere of visibility grows because more time allows more light to arrive, yet the number of visible galaxies decreases because expansion outruns that light. This contrast between a growing radius and a shrinking content can be difficult to picture. It reflects the fact that the observable universe is shaped not only by time but also by the physics of expansion. Light arrival defines one boundary, expansion defines another. These boundaries interact, creating a dynamic bubble with a shifting balance between what is revealed and what fades away. Considering this dynamic behavior can lead you to another question. If the observable bubble changes over time, what does the future observer see? Billions of years from now, hypothetical observers would see fewer galaxies. The sky would grow emptier, structure would be harder to detect. The cosmic microwave background would cool and stretch into wavelengths too long for any instrument. Their observable bubble would contain far less information than ours does. They would live in a universe that appears much simpler. They might not be able to conclude that the universe is expanding. They might not detect dark energy. Much of the evidence we use today would be inaccessible to them. This scenario highlights how fortunate we are in terms of cosmic timing. We exist at a period when expansion is measurable, when galaxies still fill the sky, and when the cosmic microwave background is detectable. The information available to us provides a unique window into the universe's history. It won't always be available. The observable bubble contains more information now than it will in the distant future. Another important point about the observable bubble is that it doesn't correspond to the region influenced by gravity or any force we exert. Our interactions extend much farther within the Milky Way and nearby galaxies, but don't reach the full observable sphere. The bubble defines what we can see, not what we can affect. It's a viewing limit, not an influence limit. The gravitational reach of our solar system is tiny compared to the size of the galaxy. The reach of the galaxy is tiny compared to the local cluster, and even that cluster is tiny compared to the observable region. So the bubble is not the region shaped by our presence, it's the region from which information has reached us. This distinction matters because some people mistakenly imagine the observable universe as our cosmic territory or region of influence. But the bubble doesn't grant any special status. It doesn't define our position. It doesn't imply importance. It simply marks where photons have arrived. Once you accept that the observable region is only part of a larger universe, it opens the door to thinking about what lies beyond. If the universe continues past our horizon, then its structure must extend far beyond the reaches of our observations. The question becomes how to imagine that large universe. Does it look similar to what we see? Does it contain similar patterns of galaxies and clusters? Or does it have regions shaped by different initial conditions, perhaps hosting variations we cannot detect? When people reach the point where the observable universe ends, they often imagine a place where everything simply stops. A line that marks the end of what exists, a kind of cosmic border, quiet and unreachable. But the horizon of the observable universe is not a frontier where reality ends. It's the distance beyond which light has not yet arrived. What lies outside it is not nothingness. It is simply more universe. Space doesn't fade away there. Matter doesn't stop existing. Physics doesn't fall apart at that boundary. The horizon is a limit created by time and expansion, not a structural edge. Understanding what lies beyond it means thinking about the universe not as a bubble with a fixed perimeter, but as something much larger, with the part we can detect representing only a slice of a far bigger whole. To imagine what lies outside our cosmic view, you can start by considering the simplest possibility. The universe looks roughly the same beyond the horizon as it does inside it. This view comes from the idea that the cosmos is homogeneous and isotropic on very large scales. Even though galaxies cluster, form filaments, and leave vast regions filled mostly with empty space, the overall pattern remains statistically uniform. No direction or location appears fundamentally different from any other. If this large-scale uniformity holds beyond the observable region, then everything continues with the same distribution. More galaxies, more clusters, more filaments, more voids. More of the same general structure that we see within our horizon, repeating itself over distances too large for light to have travelled. This possibility is the least dramatic. It treats the universe as big, consistent, and unending in its pattern. That picture works well with current observations. Everywhere we look within the observable universe, the structure becomes more even as we look across larger scales. Small scales have fluctuations, but when you observe regions hundreds of millions of light years across, the differences blend together. The universe smooths out. This smoothing supports the idea that the rest of the universe likely looks similar even if we can't see it. Nothing about what we observe suggests a drastic change just beyond the boundary where light stops arriving. But this is only the simplest scenario. The universe may be more complex. Beyond the observable region, there may be variations in the distribution of matter. Perhaps some distant areas have slightly different densities or temperatures. Perhaps some regions experience small differences in early conditions that grew into large-scale variations. We can't confirm this, but it's possible because the observable universe is only a sample. It covers an enormous volume, yet there is no guarantee it covers enough of the universe to reveal the whole. There could be superstructures larger than anything we've detected simply because they lie beyond the reach of light. Cosmologists discuss this possibility when they examine maps of the cosmic microwave background. Those maps show small fluctuations in temperature across the sky. These fluctuations reveal density differences in the early universe. The pattern is remarkably uniform, supporting large-scale smoothness, but it isn't perfectly even. There are minor imbalances. If such imbalances continue beyond the observable region, there may be areas with slightly different histories. Maybe some places underwent faster formation of structure. Maybe others have more emptiness or larger voids. The physical laws remain the same, but the arrangement of matter might shift gradually across vast distances. This would mean the universe is uniform in local behaviour, but not identical everywhere. Then there's a more speculative scenario, one that arises from the idea of cosmic inflation. Inflation suggests that the early universe expanded extremely rapidly before slowing to its current rate. That rapid expansion would have ballooned small quantum fluctuations into large-scale differences. Inside our observable region, these fluctuations appear small and consistent. But inflation predicts that regions far beyond our horizon could differ more significantly. They could have different temperatures, different densities, or different ratios of matter types. They might even be connected to variations in how galaxies and clusters form. These differences wouldn't be drastic enough to break the laws of physics, but they might create slight diversity across the larger universe. Each region would follow the same fundamental rules, but the initial conditions could vary. Some theories extend this idea further. They suggest that inflation may have produced an enormous patchwork of regions, each with slightly different conditions, not different physics, just different starting arrangements. From our perspective, our observable universe is one region among many. Those other regions don't have new laws, they just evolve differently. Perhaps some have more matter, perhaps others have less. Perhaps some regions have many more galaxies, others may be dominated by emptiness. They would still be connected as part of the overall universe, still governed by the same principles, but each would carry its own history, written by the fluctuations present when inflation began. There's also the possibility that the universe is curved in a way that makes its full structure different from how it appears locally. Our observable region appears flat. Measurements of the cosmic microwave background show no significant curvature. A flat universe can be infinite in size or finite but unbounded. If the universe is finite, it could wrap around itself in a higher dimension, much like the surface of a sphere wraps around itself in 2 dimensions. In such a case, travelling far enough in one direction might eventually bring you back to where you started. But the distances involved would be far beyond the observable bubble. The structure outside our horizon could loop in a way we can't detect. Everything we observe might be part of a repeating path, but because the full shape lies far beyond light's reach, it remains hidden. On the other end of the spectrum, the universe might be infinite. If space is infinite, then the region beyond the observable universe continues without end. It would contain countless galaxies, more than any number you could list. It would contain regions so far away that their light will never reach us. It would stretch into distances without limit. In an infinite universe, the idea of a horizon becomes even more striking. We would be seeing only the tiniest portion of an endless expanse. The observable bubble would be a minuscule fraction of the whole. Every direction would continue forever beyond our view, filled with more of the same general material that populates the visible region. In this infinite picture, there's no centre, no edge, and no special vantage point. Every location in space would be the centre of its own observable bubble, surrounded by a region of space stretching out to the limits set by light and time. This view is appealing to many cosmologists because it aligns well with the large-scale uniformity we observe. An infinite universe doesn't require unusual behaviour at the boundary because it has no boundary. The horizon remains an observational limit, not a structural one. Yet even in an infinite universe, there could be variations in how matter is arranged far beyond our reach. Infinity doesn't guarantee perfect uniformity. It simply means that the structure continues without end. Some areas could be similar to ours. Others could show differences rooted in early cosmic conditions. None of this breaks the idea of an infinite space. It simply means that the universe contains more variety than we can detect. In addition to these possibilities, there is another layer of speculation tied to the physics of the early universe. Some models of inflation propose that the universe we observe is one pocket within a larger inflating space. In these models, inflation wasn't a single, uniform event. Instead, it may have continued in other regions, creating separate pockets of space that expand independently. These pockets are sometimes described as separate regions of a larger space, each with its own observable bubble. Some might have similar physical laws. Others might have differences in their fundamental constants. This idea is often called eternal inflation. In this scenario, what lies beyond our horizon is not simply more of our universe. It could be regions that formed under slightly different circumstances. The transitions between these regions would be too distant and too stretched by expansion for any interaction to occur. These areas would be causally disconnected from ours. That means no light, no information, and no signal of any kind could cross the boundaries created by inflation. This doesn't mean they don't exist. It simply means they are beyond any possible connection. The observable bubble becomes not just a limit of light, but a limit of causality. Regions outside it are not only invisible, they are permanently out of reach. It's important to note that even this idea doesn't imply physical walls. There is no hard border separating one region from another. Instead, expansion isolates them by stretching space faster than any signal can travel. The regions drift apart forever. From our perspective, we see only our bubble. That doesn't mean it is alone. It simply means our perspective is limited. Even within more traditional cosmological models, the region beyond the horizon could contain structures vastly larger than anything we observe. We detect superclusters and filaments within our boundaries, but these structures may be part of far larger formations that extend beyond our view. Our cosmic mapping is limited by what the light can show. If a large structure spans tens of billions of light years, we might only see a small piece of it. The larger pattern remains hidden. The possibility that we live inside a small patch of a larger structure highlights why scientists are careful when drawing conclusions about the universe as a whole. Observations allow strong confidence about conditions within the bubble, but not beyond it. Theories extend those observations using physical laws. but they can't confirm what lies outside. The universe may be larger than any number we can meaningfully express, or it may be finite but curved in a way that keeps everything connected, or it may contain variations in matter, temperature, or density that we cannot detect. One of the questions people often ask is whether life exists beyond the observable universe. The limits imposed by light prevent us from detecting it even if it exists. But if the universe continues far beyond our horizon, and if it contains similar matter and similar physics, then the possibilities for worlds and environments are enormous. The number of stars and galaxies beyond our visible region could exceed anything we can measure. If life emerges naturally in certain environments, then the larger universe could contain countless locations where those conditions appear. We simply have no way of knowing. Another question concerns the fate of regions beyond our horizon. If the universe continues expanding, the distances between regions will grow. Each region becomes more isolated over time. Galaxies drift apart. Structures become unreachable. In this sense, the universe grows more fragmented, not because it breaks apart, but because expansion separates regions permanently. What lies beyond our horizon today will remain there. There will never be a future moment when that light arrives. The horizon defines what is reachable. Everything beyond it remains outside our view forever. However, some regions that are currently outside the observable bubble will become visible in the distant future. These regions lie close enough that expansion hasn't pushed them away faster than light can travel. Given enough time, their light will reach us. The horizon expands over billions of years, gradually revealing new areas. But at the same time, many existing galaxies move beyond reach due to accelerating expansion. The balance between what becomes visible and what fades away shifts over time. The picture changes slowly, shaped by both light travel and expansion. The fact that the observable universe changes over time reinforces the idea that the horizon is not a place. It is a moving limit. It grows, it shifts, and it responds to physical laws. The universe outside it remains unaffected by our viewpoint. Whatever lies beyond continues its own history, shaped by gravity, expansion, and matter. We just can't see it. This leads naturally to the understanding that the horizon divides information, not space. Everything beyond it exists in the same space as everything inside it. There is no separation. There is only a limit to what can reach us. It is similar to standing in a dark field at night with a flashlight. The objects outside the beam do not cease to exist when the flashlight fails to illuminate them. They simply remain unseen. The universe beyond our horizon behaves in the same way. It exists whether we observe it or not. When people hear that nothing can travel faster than the speed of light, it sounds like an absolute rule, a hard ceiling that sets the limit for everything in the universe. The speed of light becomes a benchmark that no object, particle, or signal can exceed. But then you hear that space itself can expand faster than the speed of light, and the picture becomes confusing. How can the universe stretch faster than the speed limit that governs everything inside it? How can galaxies move away from us at superluminal speeds without breaking the laws of physics? These questions can feel contradictory until you understand something crucial. The speed of light and the speed of expansion are not the same type of speed. They're two clocks running in the same universe, but they measure two very different things. To start untangling this, it helps to recall what the speed of light actually limits. It limits how quickly information, objects, or signals can move through space. If you try to accelerate a spaceship, no matter how powerful the engines, it can never surpass the speed of light in its local region of space. Its mass increases as it approaches the limit. The energy required becomes enormous. Physical laws prevent it from crossing that boundary. That's because the speed of light is woven into the structure of relativity. It's a fundamental constraint on motion inside space-time. But expansion is not motion through space. It is the stretching of space itself. Expansion does not push galaxies through some pre-existing medium. It increases the distance between points without requiring that any object locally exceed the speed of light. The galaxies remain nearly at rest relative to their immediate surroundings. What changes is the space between them. This difference allows expansion to behave in ways that ordinary motion cannot. Expansion can increase the distance between two far apart galaxies faster than light can travel between them, without breaking physical laws, because nothing is moving through space faster than light. The distance simply stretches. This distinction is the key to understanding why two different clocks operate in the universe, one governing local motion and one governing cosmological motion. The speed of light limits how quickly signals can travel from one point to another. The speed of expansion describes how quickly space stretches. These two rates interact constantly. Light tries to cross expanding distances, while expansion tries to grow those distances faster than light can close them. This interaction shapes the horizons we observe, defines which regions we can see, and determines which regions will never communicate with us. One way to picture this is to imagine ants walking across a rubber band. The ants walk at a constant speed along the band. Meanwhile, the band stretches. If the stretching rate is slow, the ants make progress. If the stretching rate is fast enough, the ants might fall behind, unable to move forward relative to distant marks. The ants never exceed their walking speed. They never break their own speed limit. But the surface itself expands, carrying the endpoints farther apart. In the universe, light is like the ants, moving at a fixed speed through space. Expansion is like the stretching of the band, increasing distances. You can have both operating at once without contradiction. Now imagine that the rubber band's stretching rate increases with distance. Points farther apart move away faster because there is more material between them to stretch. This mirrors how cosmic expansion behaves. Distant galaxies appear to recede faster than closer ones. The farther away something is, the more space lies between you and it, and the more stretching occurs. This is why galaxies billions of light years away can recede at speeds that exceed the speed of light, even though no physical law is broken. This effect leads directly to the idea of a Hubble radius, which marks the distance at which galaxies recede from us at the speed of light due to expansion. Anything closer than the Hubble radius can, in principle, send signals that can reach us eventually. Anything farther away recedes faster than light, yet even that boundary is not absolute. It changes over time because the expansion rate evolves. Early in the universe, expansion was influenced mostly by radiation and matter. Later, dark energy began to dominate, causing expansion to accelerate. As the expansion rate changes, the distance at which galaxies recede faster than light also changes. Even more interesting is the fact that a galaxy can be receding faster than light and still have light reach us. This seems impossible until you consider that the speed of expansion and the speed of light interact dynamically. A distant galaxy may have been receding faster than light at the moment it emitted some photons. But over billions of years, the expansion rate changed. The photons could gradually make progress toward us as conditions shifted. They might eventually cross a shrinking region, where space expands slower than the speed of light. This allows photons from extremely distant galaxies to reach us even though, at some moments, the galaxies themselves receded faster than the speed of light. This interplay shows that the universe doesn't have one simple boundary where light either can or cannot reach us. Instead, the boundary depends on how expansion changes. The observable universe is shaped partly by how far light can travel and partly by how expansion evolves. Two clocks, not just one, set the limits. The next step in understanding this relationship is to look at how expansion actually works. Expansion is described by a mathematical function called the scale factor, which changes with time. The scale factor determines how distances between points in space evolve. When the scale factor grows, space expands. When it grows faster, expansion accelerates. The growth rate of the scale factor is known as the Hubble parameter. This parameter isn't constant. It changes as the universe evolves. Early in cosmic history, the universe expanded rapidly. Then expansion slowed as gravity from matter pulled things inward. Billions of years later, expansion began to accelerate again as dark energy became dominant. This means that the speed of expansion at any moment depends on the contents of the universe and its history. It's not a single value, it's a dynamic process. By contrast, the speed of light is constant. It does not change with time. It does not depend on energy density or matter. It remains fixed at every moment in every location. This constancy is part of what defines relativity. So you have one speed, expansion, that changes with the history of the universe, and another speed, light, that stays constant no matter what happens. When you put them together, you get moments when light can make progress against expansion, and moments when expansion outruns light. These moments are extremely important. They determine which regions of the universe can communicate. When expansion is slow relative to the speed of light, signals can cross vast distances. When expansion accelerates, those distances grow faster, isolating regions from one another. This changing relationship creates horizons. A horizon forms where expansion prevents light from traversing the gap. That horizon isn't a wall, it's a limit produced by these two competing clocks. You can think about this by imagining a race between two runners. Light always runs at the same speed. Expansion changes pace. Sometimes expansion is slow, sometimes fast. In the early universe, expansion raced ahead quickly. Then it slowed. Later, it sped up again. Depending on when a photon is emitted, it may find itself in a race it can win, or a race it loses. The result of this constant competition is a boundary between regions we can eventually see and regions we can never see. This boundary brings up an important point. Even though we often talk about the universe having a size defined by the observable horizon, this horizon is not a physical limit to space. It's simply the limit of where photons have managed to win the race against expansion over the age of the universe. If expansion had slowed more or less at certain points, the observable horizon would be different. It isn't fixed by the universe's structure. It is set by the interplay between light and expansion. One of the most interesting consequences of this is that the observable universe is not the same for every observer. Someone in a distant galaxy would have a horizon centered on their position. Their visible sphere would include regions we cannot see. It would exclude regions we can. Their horizon might include some galaxies currently moving away from us faster than light. Their horizon is shaped by local conditions, just as ours is shaped by our position. Expansion acts everywhere, and light acts everywhere, so each location has its own race between the two. Another key point is that the speed of expansion is not directly measurable in the same way the speed of light is. You don't watch a galaxy move past you across some cosmic background. You infer expansion from redshift, from the stretching of light. The stretching isn't motion through space, it's the result of the expansion of space. When light's wavelength becomes longer, it tells us that space expanded while the photon travelled. This stretching provides evidence that expansion operates on cosmological scales. It doesn't act on galaxies or atoms, it acts on the vast distances between them. This brings us to an interesting concept. When distances become large enough, expansion dominates everything else. Even gravity can't hold structures together if they're too far apart. That's why galaxies and clusters stay gravitationally bound, but clusters themselves drift apart from other clusters. Expansion controls the large-scale structure, and at the largest scales, it sets a boundary beyond which even light cannot travel fast enough to maintain contact. This boundary is sometimes called the cosmic event horizon. It marks the limit of regions that can send signals we will eventually receive. Anything beyond that horizon is permanently out of reach. That doesn't mean it stops existing. It simply means expansion prevents any future communication. This horizon is shaped entirely by the relationship between the speed of light and the rate of expansion. If expansion accelerates, the horizon becomes smaller in terms of what regions can eventually be seen. If expansion slows, more regions might become reachable. This dynamic shows why cosmology often talks about the future of the observable universe. Over billions of years, the cosmic event horizon determines what remains visible. As expansion accelerates, more galaxies drift beyond the horizon. Someday, only a small region of space around our local cluster will remain visible. Everything else will fade away. That fading doesn't result from light getting dimmer, it results from expansion outpacing communication. The galaxies will still exist, they just won't be able to send light to us. In this future scenario, the night sky changes. It becomes emptier. It loses the distant galaxies that currently fill the deep field images. The observable bubble shrinks in what it contains even as its radius increases. Light from new regions continues to arrive, but the number of galaxies within reach decreases. The two clocks, light and expansion, continue their race, with expansion winning more of the time as dark energy dominates. This raises another question. If expansion can exceed the speed of light, why can't objects travel faster than light through space? The answer lies in how relativity defines motion. Light's speed limit applies to anything carrying information or mass through space, but expansion doesn't carry information. It doesn't move objects through a medium, it simply changes the metric that defines distance. When the metric expands, distance increases without requiring motion. The galaxies aren't moving through space at superluminal speeds. Space is increasing between them. That's why relativity remains intact. This difference becomes even clearer when you consider that expansion affects objects differently, depending on their distance from one another. Expansion has almost no effect at small scales. The solar system stays bound. The galaxy stays bound. Gravity holds these systems together more strongly than expansion can pull them apart. But at large scales, expansion dominates. The force of expansion is incredibly weak locally, but it accumulates across billions of light years. That accumulation allows expansion to outrun light at sufficiently large distances. The contrast between local behavior and cosmic behavior highlights the importance of understanding the scale at which expansion operates. If you tried to measure expansion inside a room, you would find nothing. Even the most sensitive instruments cannot detect expansion at human scales. Only when you examine galaxies tens or hundreds of millions of light years apart does the effect become noticeable. It grows with distance. That's why it is often said that expansion is not a force in the usual sense. It is a property of space-time on large scales. One of the profound implications of these two clocks is that the universe's history cannot be understood by looking only at present distances. You need to understand how expansion evolved. Light that reaches us today may have crossed regions of space that expanded faster or slower at different times. The path of that light is shaped by these conditions. If you imagine a photon emitted shortly after the Big Bang, it travelled through a universe that was first extremely dense, then expanding rapidly, then slowing down, then accelerating again. Each phase influenced how far it travelled and how much it stretched. The photon carries this entire history in its wavelength. When astronomers study these wavelengths, they decode the race between light and expansion across billions of years. This decoding allows researchers to reconstruct the universe's expansion history. It tells them when matter dominated. It tells them when radiation dominated. It shows when dark energy began to influence expansion. Without the speed of light serving as a fixed clock, none of this would be interpretive. Without expansion altering distances, none of this would be dynamic. The two clocks together define the structure of cosmic history. Thinking about the universe in this way opens up a clearer picture of why some regions will always remain beyond reach. The speed of light sets a universal speed limit, but expansion can stretch distances faster than that limit. The regions where expansion wins the race become permanently hidden. The regions where light wins become part of the observable universe. There is no conflict between the rules. They simply describe two different aspects of the cosmos. Most of the stars you see appear steady and bright, sending their light across the darkness with no sign that anything unusual is happening. The Milky Way stretches above like a faint band, and nothing about that view suggests that galaxies are slipping away from us, drifting toward distances where their light will no longer reach Earth. Yet that is exactly what is happening. Across the universe, countless galaxies are gradually moving beyond the point where their light will ever arrive. The reason isn't that they're dimming or shutting down, it's that the fabric of space itself stretches, carrying them farther away, and in the process, stretching their light as well. This stretching is called redshift, and it tells one of the most important stories in cosmology. It explains not only how far away galaxies are, but how long their light has travelled, how much the universe has expanded during that journey, and whether those galaxies will eventually drift beyond reach. Redshift is a simple idea with profound meaning. When light travels through a universe that expands, its wavelength stretches along with space. A wave of light that leaves a galaxy at one wavelength arrives at a longer wavelength if space grew during its journey. Longer wavelengths correspond to lower energy. Visible light can shift into infrared. Infrared can shift into microwaves. Microwaves can shift into radio waves. The light reddens, not because the object changed colour, but because space expanded while the photon was on its way. This stretching gives astronomers a direct measurement of how much the universe has grown since the light was emitted. The farther away a galaxy is, the larger the redshift. This relationship creates a direct link between distance and the stretching of light. The importance of redshift becomes clear when you think about how light moves through an expanding universe. If space was static, light would travel in straight lines, retaining its wavelength. But space isn't static, it stretches. That stretching acts on the wavelength of the photon, which is why more distant galaxies appear more redshifted. The more time light spends travelling, the more expansion affects it. Redshift becomes a way of reading the universe's expansion history. Each photon carries a record of how much space stretched during its journey. This record reveals that galaxies farther away have higher redshifts. Their light has been stretched more because it travelled longer and encountered more expansion. This correlation allows astronomers to estimate distances based on redshift measurements. If a galaxy has a high redshift, it's far away. If it has a moderate redshift, it's closer. But redshift is not just about distance, it's also about time. A galaxy with high redshift appears as it was billions of years earlier. A galaxy with moderate redshift appears as it was more recently. Redshift weaves together space and time, turning every distant light source into a time capsule. But redshift also reveals something else, something more subtle and more profound. Over extremely large distances, expansion becomes so strong that galaxies drift away faster than light can cross the growing gap. When that happens, the light from those galaxies can never reach us. They fall beyond what's called the cosmic event horizon. This horizon marks the limit of what can ever send light to us, no matter how long we wait. Galaxies beyond this horizon remain forever hidden. They still exist, still evolve, still form stars and structures, but their light will never arrive here. Redshift plays a central role in identifying which galaxies are drifting toward that horizon. As galaxies move away faster, the stretching of space increases the redshift of their light. When the redshift becomes extreme, the galaxy's signal dims dramatically. Eventually, its light spreads into wavelengths so long that our instruments can barely detect them. Before a galaxy fully crosses the horizon, it begins to fade from view. Its light becomes stretched into faint, low-frequency radiation. The last photons arrive one by one, stretched to near invisibility. Then no more arrive. The galaxy hasn't vanished. It hasn't reached an edge. It has simply moved out of communication range. This fading is not sudden. It's slow, drawn out over billions of years. A galaxy doesn't disappear like a candle going out. Instead, it recedes gradually as the universe stretches the space between us and it. The redshift grows, the brightness decreases, the galaxy slides toward longer wavelengths. Eventually, the signal becomes too weak and too stretched to detect. The process is driven entirely by expansion, acting on light during its long journey. This raises an interesting question. Why does redshift affect brightness? The answer lies in how light spreads out over distance, and how expansion modifies that spread. When a galaxy emits light, the photons travel outward in all directions. The farther they go, the more spread out they become. That naturally decreases brightness. But in an expanding universe, each photon also loses energy as its wavelength stretches. Longer wavelengths mean lower energy. So the brightness fades not only because the photons spread out, but because each photon carries less energy by the time it arrives. This double effect explains why distant galaxies are so faint. They aren't dimming. Their light is being stretched thin. Light stretching thin in this way isn't just a nuisance for astronomers. It offers crucial information about the fate of the universe. The more the redshift increases, the more expansion has influenced the photon's journey. When redshift reaches extremely high values, it indicates that expansion is dominating over light's ability to travel. This domination signals that the region emitting the light may eventually move beyond reach. The galaxy becomes part of the unreachable universe, permanently beyond communication. This situation can be confusing because it creates a difference between what we can see now and what we can ever see in the future. Some galaxies that are visible today will eventually drift beyond the event horizon. Their light reaches us now only because they emitted those photons before they crossed the threshold. Once they move far enough away due to accelerating expansion, future emissions will never reach us. We are witnessing the final moments in which we can detect them. Their current light represents the last messages they can send before expansion wins completely. The idea that galaxies can fade out of our observable universe is one of the more surprising implications of redshift and expansion. It means our cosmic view is temporary. The deep field images we take today capture galaxies that future observers won't be able to see. In the far future, the universe will appear emptier not because galaxies died out, but because light from distant galaxies will no longer reach observers in our region. Redshift shows this process developing over time. Another reason galaxies fade is that redshift pushes their light into wavelengths our instruments struggle to detect. When photons stretch into the microwave or radio range, their energy becomes extremely low. Even the most sensitive detectors have limits. The universe is full of background radiation and noise. Picking out the faint signatures of ancient galaxies becomes harder as redshift increases. Eventually the signal falls below the noise floor. The galaxy still sends light, but expansion stretches it so much that the signal becomes buried. This effect is similar to listening to a distant voice in a noisy room. As the person speaking walks away, their voice becomes fainter. Eventually, the noise overwhelms the sound. You can no longer distinguish their words. They haven't stopped speaking. You just can't detect their voice over the competing noise. In the universe, redshift pushes galaxy light into ranges where background radiation becomes dominant. The signal fades not because it stops, but because the stretching separates it from detectability. This gradual loss of visibility highlights something important about redshift. It is not just a measure of distance, it is a measure of how expansion affects the journey of light. The more expansion has occurred, the greater the redshift. The greater the redshift, the more the light is dimmed and stretched. Redshift becomes the indicator of the universe's history. It shows how expansion evolved over time. One of the most fascinating aspects of redshift is that it doesn't only reflect the current rate of expansion, it reflects the integrated expansion during the entire time the photon travelled. That means a photon might have left its galaxy when expansion was slow, then passed through an era when expansion accelerated, then crossed regions where expansion changed again. Each phase contributes to the redshift. The photon accumulates the history of expansion in its wavelength. When astronomers measure that wavelength, they measure that history. This connection between light and expansion forms the basis for understanding the universe's growth. When redshift increases linearly, it suggests a consistent expansion rate. When redshift increases non-linearly, it indicates that expansion changed. The discovery that distant galaxies had higher redshifts than expected was one of the clues that expansion began accelerating billions of years after the Big Bang. Without redshift, this discovery would have been impossible. The universe's expansion history is written into the fading light from distant galaxies. Redshift also plays a role in how astronomers estimate the size of the observable universe. When they measure redshift, they can determine how long the light travelled. When they know how long it travelled, they can estimate how far away the galaxy was when it emitted the light. Then they must account for how much space stretched afterwards. This calculation reveals the current distance. Without redshift, these distance estimates would be impossible. We would have no way of knowing which galaxies lie near the horizon. We wouldn't know which galaxies are slowly drifting beyond reach. Redshift shows that some galaxies are receding faster than light. That fact alone is not enough to determine whether their light will ever reach us. A galaxy might currently be receding faster than light due to expansion, but if expansion slows in the future, its photons might eventually cross the gap. But when expansion accelerates, galaxies that cross a certain distance become unreachable forever. Their redshift continues increasing even as their light dims. At a certain point, their redshift indicates that they have crossed the cosmic event horizon. No light emitted after that moment will ever reach us. This crossing is not something we can observe directly. We can't see a galaxy move beyond the horizon because the horizon is defined by the relationship between light and expansion. But redshift gives a signal of when a galaxy is approaching that boundary. Once redshift reaches sufficiently high values, the galaxy's light becomes stretched into wavelengths that are difficult to detect. The galaxy glows faintly in the infrared or microwave. Eventually it becomes invisible. By the time the galaxy fully crosses the horizon, it's been invisible for a long time. Redshift tells us this fade-out is occurring. Another aspect of redshift is how it shifts the appearance of distant galaxies. A galaxy that forms stars at a high rate may emit intense ultraviolet light, but if it lies at a great distance, that ultraviolet emission can shift into the visible range by the time it reaches us. The visible light might shift into infrared. That infrared might shift into microwave. This shifting alters how astronomers interpret observations. A galaxy that appears red or infrared might not be intrinsically red. It might be so distant that its blue or ultraviolet light has been stretched. Without understanding redshift, you might misinterpret the galaxy's properties. Redshift helps reveal what the galaxy actually looks like in its own frame. This stretching also affects how we perceive the universe's earliest galaxies. The earliest galaxies were small, chaotic, and full of young stars. They emitted intense light, but because they lie at extreme distances, their light is highly redshifted. Modern telescopes detect them in infrared. As technology improves, more of these early galaxies become visible. But even with advanced instruments, the increasing redshift of distant galaxies limits what we can detect. Eventually, light becomes too stretched to observe. This limitation helps explain why there is a practical horizon even before the cosmic event horizon. Technological limits create a detection threshold. Cosmic microwave background radiation forms the earliest visible wall, not because the universe ended there, but because light from earlier times cannot travel freely. Redshift pushes signals into wavelengths beyond our current detection methods. Even if the universe were static, this barrier would exist. But expansion stretches it farther. The earliest light becomes longer in wavelength over time. Other distant signals fade in the same way. These effects combine to create a universe where more distant galaxies appear progressively fainter and more stretched. Eventually, all distant galaxies that are beyond a certain redshift threshold will disappear from our view. They will drift into darkness from our perspective. Even though they continue to exist, they won't vanish from the universe. They will vanish only from our visibility. The notion that galaxies can drift away beyond detection brings the idea of cosmic isolation into focus. Over extremely long timescales, observers in our region will see fewer and fewer galaxies. The night sky will lose its distant signals. The universe will appear smaller not because it shrinks, but because the light from distant regions will no longer arrive. Redshift gradually hides the universe beyond our horizon. It doesn't erase it, it simply separates us from it. Understanding how redshift hides galaxies sets the stage for exploring another topic. If distant galaxies fade as their light stretches into long wavelengths, what signals remain from the earliest universe? What light still reaches us from regions far beyond any galaxy? When you think about the most distant light in the universe, you might imagine the glow from ancient galaxies or the faint signals from stars that formed billions of years ago. But the farthest light we can detect doesn't come from stars or galaxies at all. It comes from a time before the first stars were born, before galaxies formed their spirals and clusters took shape. It comes from a moment so early that the universe had only just become transparent enough for light to travel freely. This faint glow, stretched into microwave wavelengths by the expansion of space, fills the entire sky. It comes from every direction, not from any single object. It's called the cosmic microwave background, and it represents the earliest visible moment in the universe's history. Learning to listen to it is learning to observe the farthest edges of what light can show us. The cosmic microwave background is not a boundary. It isn't a wall. It isn't a surface you could touch or a shell surrounding us. It is a layer of light from a time when the universe cooled enough for photons to move without being scattered constantly by charged particles. Before that moment, the universe was too hot, too dense, and too filled with ionized matter for light to travel very far. Photons bounced around repeatedly in a fog of electrons and protons. Space was not dark, but it was opaque. Light couldn't move in straight paths. As the universe expanded and cooled, electrons and protons combined to form neutral atoms. That transition allowed light to pass through space for the first time. The photons from that era have been travelling ever since, gradually cooling, stretching, and shifting into microwaves. This light creates an image of the universe as it was roughly 380,000 years after the Big Bang. Compared to the universe's age of 13.8 billion years, that moment is incredibly early. It's the earliest visible moment because earlier than that, light simply couldn't travel freely. The cosmic microwave background is the earliest signal the universe can send us. What makes this light remarkable is that it arrives from every direction, forming a smooth background of microwaves. It's not bright. In fact, it's extremely faint. You wouldn't notice it without specialized equipment. But this faint light contains an extraordinary amount of information. It carries the temperature of the early universe with remarkable precision. It reveals tiny fluctuations in density, fluctuations that eventually grew into galaxies, clusters, and the large-scale structure of the cosmos. These small differences in temperature show where matter was slightly more concentrated. Over billions of years, gravity amplified those small differences. Listening to the cosmic microwave background is like listening to the earliest whisper of structure in the universe. The uniformity of this microwave glow is important. It tells us that the universe at that early time was nearly the same temperature everywhere. The temperature differences are incredibly small, only a few millionths of a degree. This smoothness supports the idea that the universe expanded rapidly early in its history. Rapid expansion would smooth out irregularities and create the uniformity we observe. The tiny fluctuations that remain are the seeds from which all later structure formed. Those fluctuations are not random noise. They follow a pattern that aligns with predictions made by models of early cosmic inflation. Inflation suggests that the universe expanded extremely quickly during a brief period shortly after the Big Bang. This rapid stretching would create the uniformity we see in the cosmic microwave background. It would also produce the specific pattern of fluctuations observed today. These fluctuations encode the early universe's density variations and help scientists understand its early conditions. Listening to the cosmic microwave background is like looking at a photograph of the universe when it was still forming its basic structure. The image reveals regions that were slightly warmer or cooler. The warmer regions correspond to slightly denser areas. The cooler regions correspond to less dense areas. Over time, gravitational attraction caused the denser areas to collapse into galaxies and clusters. The less dense areas became voids. The structure of the entire universe today traces back to these fluctuations. This connection means that the cosmic microwave background isn't just the farthest light we can see. It is the foundation of everything we observe. The arrangement of galaxies, the formation of clusters, the distribution of matter, all of it began with these tiny variations. By studying the distribution of temperature differences, scientists infer the amount of matter in the universe, the amount of dark matter, the behavior of dark energy, and the shape of the universe. This faint echo becomes a map of the cosmos's earliest blueprint. Another important aspect of this light is that it shows us how the universe expanded. The wavelengths we detect today reflect how much space stretched. Originally, this light was far more energetic, close to the range of visible or infrared. As space expanded, the light stretched into microwaves. The more it stretched, the cooler the background became. Today, the cosmic microwave background has a temperature of about 2.7 degrees above absolute zero. That temperature is uniform across the sky to an extraordinary degree. It serves as a kind of cosmic thermometer, telling us how much the universe has grown. This uniformity actually creates a puzzle. If the universe is so large that different regions were never in contact before they emitted this light, how did they reach the same temperature? Two distant points that couldn't exchange information should have different temperatures, yet the cosmic microwave background shows that everything had the same temperature at that early moment. This puzzle is known as the horizon problem. Inflation solves it by suggesting that all regions were once close together before inflation rapidly expanded the universe, carrying them far apart. Listening to the cosmic microwave background gives scientists direct evidence for this inflationary phase. The fluctuations in the microwave background have specific patterns that match inflation's predictions. These patterns are not random. They reflect sound waves moving through the dense plasma of the early universe. When the universe was opaque, pressure differences caused waves to move through the matter, creating alternating regions of higher and lower density. When the universe became transparent, those patterns froze into place. We see them today as slight variations in temperature. These waves provide a way to study the early universe's behavior in detail. The cosmic microwave background also reveals the curvature of the universe. The way light from this era is distributed across the sky tells scientists whether space is flat, curved like a sphere, or curved like a saddle. Measurements indicate that the universe is extremely close to flat. This is another piece of evidence for inflation. Inflation flattens space, stretching any curvature to near invisibility. Even though the cosmic microwave background comes from a time long before galaxies formed, it helps explain how galaxies eventually appeared. These slightly denser regions shown in the background attracted more matter over time. That matter collapsed into stars, clusters, and large structures. The cosmic microwave background is like a snapshot of the universe's potential. It shows the earliest outlines of how structure would develop billions of years later. This early light also shows how much matter the universe contains. The size and shape of the fluctuations reveal how much ordinary matter existed at that time. They also reveal the amount of dark matter. Dark matter does not interact with light, but it does influence the motion of matter. By studying the fluctuations, scientists infer how much dark matter was present. The cosmic microwave background becomes a tool for understanding invisible components of the universe. In addition to matter, the cosmic microwave background reveals information about dark energy. Dark energy affects the rate of expansion. Its influence becomes stronger over time. The data from the cosmic microwave background, when combined with observations of galaxies and supernovae, helps scientists understand how expansion has changed. It helps explain why expansion began accelerating several billion years after the Big Bang. Listening to this early light allows scientists to measure the age of the universe. When they analyse the temperature distribution and compare it to theoretical models, they find that the age of the universe is about 13.8 billion years. This estimate comes from how well the data matches predictions about the early universe's density and expansion rate. Without the cosmic microwave background, determining the age would be far more difficult. One of the most compelling features of the cosmic microwave background is that it comes from the same distance in every direction. This doesn't mean Earth lies at the centre of the universe, it means the light comes from a moment in time. Wherever you are in the universe, if you look far enough into the distance, you reach the same moment. The moment the universe became transparent. This creates a spherical boundary of visibility for every observer. That boundary is not a spatial edge. It is a temporal marker. It shows a moment in cosmic time, not a place in cosmic space. This is why the cosmic microwave background appears as a sphere around every observer. Someone in a distant galaxy would see the same glow surrounding them, centered on their position. Their sphere overlaps with ours, but is not the same. Every observer has their own visible region defined by the path light takes to reach them. The cosmic microwave background forms the outermost layer of that region. It marks the earliest chapter that visible light can tell. This idea sometimes leads people to imagine that beyond the cosmic microwave background lies something different or unknown. But the universe beyond that light is simply the universe at earlier times, at temperatures too high for light to escape. There is no edge there. There is no barrier. There is only a transition between transparent and opaque conditions. If you could move far enough away from your current location, the cosmic microwave background would shift. You might see different features, but the boundary itself would always represent the same moment in cosmic time. What lies beyond the cosmic microwave background is the universe at an even earlier stage. But because light from that stage cannot travel, we cannot observe it directly. We can infer what happened. We can model it. But the light itself carries no information from before that era. Listening to the cosmic microwave background tells us the earliest visible story, but it does not reveal everything. Yet even this limitation holds value. It reminds us that the universe's earliest moments require different tools. We rely on particle physics, quantum theory, and mathematical models to understand what happened before the universe became transparent. The cosmic microwave background marks the boundary between what light can show directly and what must be inferred indirectly. Despite being the earliest visible light, the cosmic microwave background does not fade or disappear. It persists, filling the sky with a uniform glow. Over time, as the universe expands, its temperature continues to decrease. It shifts to even longer wavelengths, but it remains detectable. Far in the future, it will cool further, moving into extremely long wavelengths. Observers billions of years from now might struggle to detect it, but today it remains one of the clearest windows into the distant past. The cosmic microwave background is not the only echo of the early universe, but it is the strongest. It carries the most detailed information. It forms the clearest boundary of what light can reveal, and because it stretches across the entire sky, it provides a map of the early universe that no single galaxy could match. Cosmic inflation often sounds like a distant technical idea, a burst of rapid expansion in the early universe, a mathematical concept described in textbooks and research papers. But the aftermath of inflation influences everything we see in the cosmos today, including the boundaries we talk about when we mention horizons, observable regions, and the limits of how far light can reach. These boundaries didn't come from walls or edges built into the universe. They emerged from the conditions that inflation created. Understanding how these boundaries were born means looking carefully at what inflation did to space, time, matter, and the possible structure of regions far beyond our sight. Inflation refers to a period in the earliest moments of the universe when space expanded much faster than it does today. This expansion didn't push matter outward in the way an explosion does. Instead, it stretched space itself. Tiny quantum fluctuations were pulled across enormous distances. Regions that were once close became separated faster than light could travel. That doesn't violate relativity because nothing moved through space faster than light. Space itself expanded. This rapid expansion shaped the large-scale features of the universe we see today. When inflation ended, the universe didn't shrink back. The distances that inflation created remained. Regions that became too far apart never reconnected. Whatever happened in one region of space after inflation no longer affected distant regions. Inflation froze the structure of the universe on enormous scales, locking in differences that might have been tiny beforehand. These differences became the seeds for galaxies, clusters, and cosmic patterns that formed billions of years later. One of inflation's most important consequences is that it smoothed out the universe. Before inflation, quantum scale fluctuations existed as natural variations in density. When space expanded rapidly, these small variations were stretched into large-scale variations. But because inflation erased larger irregularities and created uniform conditions across vast distances, the universe that emerged afterward was remarkably even. Every region had almost the same density and temperature. The cosmic microwave background shows this uniformity. The tiny temperature differences we detect now come from those original quantum fluctuations that inflation stretched. Because inflation smoothed the universe so effectively, the boundaries we talk about today are not places where something changes suddenly. They're consequences of how far light can travel and how inflation separated regions. There is no surface marking the end of the universe. There is no border created by structure. Instead, inflation created distances so large that light has not had enough time to cross them. What we call boundaries are really limits created by time and the expansion rate. Inflation's aftermath explains why these limits exist in the first place. To understand this, imagine that inflation hadn't happened. The universe would have expanded much more slowly from the beginning. Light and matter would have had more time to travel between regions. Temperatures might have varied dramatically across space. Different regions might have had very different properties. The universe might not look uniform at all. Without inflation, the cosmic microwave background might show huge variations instead of tiny fluctuations. Galaxy formation might have happened differently, with large-scale patterns showing distinct irregularities. But inflation smoothed out these possibilities. It created a universe where the differences between regions were small enough to grow gradually over billions of years. Yet even as inflation smoothed the universe, it created the conditions that generate boundaries today. When inflation ended, space was already enormous. Regions separated by inflation could no longer exchange light or signals because the distances between them were too large. Expansion continued, but at a slower rate. Light began to travel freely once the universe cooled enough for neutral atoms to form. But the distances set by inflation were already far ahead of light's ability to cross them. Those enormous separations became permanent. This created regions that are causally disconnected, not because they are separated by walls, but because inflation placed them too far apart for light to bridge the gap. These disconnected regions form the backdrop for why we speak of horizons. A horizon isn't a physical structure. It's the distance beyond which signals can't reach us. Inflation made that distance very large. Without inflation, our horizon might be far smaller, and the universe we see today would be shaped by very different conditions. Inflation also explains why the observable universe is only a fraction of the whole. The region we can see is determined by how far light has travelled since the universe became transparent, but inflation stretched the universe so much that the region beyond our visible sphere is immense. Light from those regions hasn't had time to reach us. Even if the universe is infinite, we can only see a finite part because inflation expanded space enormously before ordinary expansion began. There's another result of inflation that helps explain boundaries. Inflation didn't just stretch distances, it also amplified the quantum fluctuations that eventually form the cosmic structure we observe. These fluctuations became the seeds for galaxies and clusters. The slightly denser regions pulled in more matter. The slightly less dense regions became voids. The pattern of these fluctuations is preserved in the cosmic microwave background. It shows that inflation didn't produce a perfectly uniform universe. It produced one that was nearly uniform with slight variations. Those tiny variations grew over billions of years to produce everything we see today. These early patterns form something like a cosmic fingerprint. They reveal how inflation behaved. They show the scale at which inflation stretched fluctuations, and they reveal how inflation influenced the distribution of matter at the larger scales. This fingerprint also tells us that inflation must have been incredibly rapid. Only a rapid expansion could create a universe where the temperature is nearly the same everywhere and where fluctuations are so small. Because inflation happened so early and so fast, the boundaries created by it are enormous. These boundaries aren't physical divisions between regions, they are differences in distances too large to cross. Inflation created a universe where billions of light years separate regions in ways that ensure permanent isolation. Even if we had infinite time, we could never observe those regions. Inflation placed them beyond our horizon permanently. This leads to another interesting point. In many models of inflation doesn't stop everywhere at once. It stops in some regions while continuing in others. That means some areas of the universe continue expanding at tremendous rates, while other areas slow down. The areas where inflation ends become what we observe as local universes. These are not separate universes in a strict sense. They are regions where inflation ended, and where the hot, dense conditions of the early universe gave rise to galaxies and matter. Other areas might still be inflating, expanding faster than any signal could ever travel. These expanding regions remain forever beyond our reach. In this view, the universe consists of many regions where inflation ended at different times. Each region evolves independently. Each region might contain galaxies, stars, and structures similar to ours. But the regions are separated by vast distances that inflation continues to stretch. They remain disconnected. This picture helps explain why we talk about horizons rather than edges. The boundaries produced by inflation aren't edges where space stops. They are limits where expansion dominates over communication. Some variations of inflation take this idea further. They suggest that inflation might create regions with slightly different physical conditions. These differences are subtle. They do not violate the basic principles of physics, but they may create variations in the density of matter, the rate of early expansion, or the distribution of fluctuations. These differences might lead to regions that look different from ours on large scales. We can't observe these regions because inflation placed them too far away, but the idea that inflation could produce diversity within the universe is a natural extension of how inflation behaves. Understanding how inflation creates boundaries also helps explain why the cosmic microwave background looks so uniform. Inflation stretched any irregularities across enormous distances. It erased large-scale differences. Only small-scale fluctuations remained. Those fluctuations became the seeds of structure. Without inflation, the early universe might have been uneven, creating large variations in temperature and density. But inflation created the conditions that made the universe appear smooth and flat on the larger scales. One result of this smoothing is that the universe looks nearly flat. Measurements of the cosmic microwave background show that space is very close to flat on large scales. Inflation predicts this. Rapid expansion would stretch any curvature out of existence. If space had been curved like a sphere or a saddle before inflation, that curvature would be stretched so much that it would appear flat afterward. This is exactly what we observe. The universe may have a slight curvature we can't detect, but inflation explains why space looks flat across the observable region. Another result is that the universe appears homogeneous on large scales. Homogeneous means that matter is distributed evenly when viewed from a broad perspective. Inflation helps explain this uniformity. Without inflation, different regions might have had different temperatures or densities. But inflation smooths these differences so thoroughly that the universe emerging from it looks consistent everywhere within the observable region. The aftermath of inflation also influences how we think about the size of the universe. Inflation suggests that the universe could be much larger than the region we observe. It may be infinite, or it may be finite, but extremely large. In most models, the region we see is tiny compared to the full universe. Light has only had time to travel a limited distance since the universe became transparent. Inflation ensures that regions beyond that distance remain hidden. This leads to interesting possibilities. If inflation extended far enough, the universe might be so large that any pattern seen in our region could appear again elsewhere. If the universe is infinite, every possible arrangement of matter could occur somewhere. These possibilities arise not because the universe has edges or boundaries, but because inflation created an enormous space whose full extent we cannot observe. Some people imagine that inflation's aftermath created multiple universes, separate and disconnected. But in cosmology, these are not universes in the strict sense. They're regions of one larger universe that inflation separated. These regions never interact because inflation placed them too far apart, but they share the same physical reality. They are part of the same overarching structure. The boundaries between them are not physical dividers. They are distances light cannot cross. Thinking about boundaries created by inflation helps clarify why our observable universe looks the way it does. We see only the regions where light has arrived. We see the structures built from fluctuations amplified by inflation. We see the uniformity inflation created, but we do not see the full universe because inflation placed enormous distances between different areas. These distances remain larger than the limits set by light and expansion. This perspective shifts how we understand cosmic limits. The boundaries we observe are not signs of a contained universe. They are the results of inflation stretching. They are the distances that light has not had enough time to cross. They are the edges of visibility, not the edges of existence. Inflation created those boundaries by shaping the distances and initial conditions that define the universe's evolution. When people hear the word multiverse, they often imagine something dramatic. Parallel worlds stacked like pages in a book, different versions of themselves living out different lives, infinite realities splitting apart with every decision. Popular culture presents these ideas in vivid ways, sometimes close to science, sometimes far from it. But in cosmology, when researchers talk about the possibility of a multiverse, the idea usually begins in a quieter, more technical place. It begins with inflation. The same inflation that shaped our observable universe, smoothed its early conditions and amplified its fluctuations, might also have created something far larger and more complex than anything we can observe. In this picture, what lies beyond our cosmic horizon isn't just more of the same universe. It could be regions with their own histories, their own conditions, and their own forms of development. To understand why scientists consider this possibility seriously, you need to look at how inflation behaves in theoretical models. Inflation describes a process in which space expanded extremely rapidly in the early universe. In most versions of the theory, inflation does not end everywhere at the same time. Instead, it ends in some regions while continuing in others. A region where inflation ends becomes a place where the hot, dense state of the early universe forms, eventually leading to galaxies, stars, and everything else. But beyond that region, inflation continues. Those areas still expand at extraordinary rates, stretching farther and farther away. Eventually, inflation stops in another pocket. That pocket also becomes a region filled with matter and radiation. If inflation continues indefinitely in some areas while ending in others, the result is a universe divided into many regions that grew from different pockets. Each region could be enormous, far bigger than our observable universe. In this picture, our observable universe is one such pocket. Outside our pocket lies an immense expanse, where inflation still operates, or where inflation ended in different ways. These areas are not separate universes in the traditional sense. They are parts of the same overall space but disconnected from each other by distances too great for light to cross. Each region experiences its own evolution, shaped by how inflation ended there. Some might look similar to ours, others might differ in subtle ways. In some models, the differences could be substantial. This idea can sound exotic, yet it arises naturally from the mathematics of inflation. Once inflation begins, it tends to continue unless something specific stops it. The conditions required to end inflation may occur locally rather than globally. That means inflation could end in one region, while continuing everywhere else. The ongoing inflation stretches those other regions so rapidly that nothing from them can reach us. Light cannot travel across the expanding distances, signals cannot move between pockets, even gravity cannot bridge the gap. The separation becomes permanent. This scenario is sometimes called eternal inflation. It doesn't mean inflation lasts forever everywhere. It means inflation continues indefinitely in some areas, even while ending in other areas. Those areas where inflation ends become what we observe as populated regions with galaxies and clusters. In this view, the broader universe contains countless such regions, each separated by distances that grow faster than light can travel. They remain disconnected due to expansion, not due to any physical barrier. The idea of eternal inflation leads to a natural multiverse concept. Each region where inflation stops becomes one bubble of post-inflationary space. These bubbles can be extremely large. Some may have conditions nearly identical to ours. Others may differ because the details of inflation's end vary slightly. These differences might involve the distribution of matter, the temperature at which inflation ended, or the physical constants that govern forces and particles. In ordinary cosmology, these constants appear fixed, but in certain theoretical models the values could differ slightly from one region to another if inflation ended in different conditions. It's important to note that this multiverse idea doesn't arise from the desire to imagine exciting scenarios. It arises from trying to understand inflation consistently. Many inflation models naturally produce multiple regions. The observable universe becomes one example among many. The broader structure becomes far larger than anything we can observe directly. If inflation worked the way many models predict, our visible region is simply a small piece of a far greater whole. Despite this, the multiverse idea faces a challenge. It cannot be observed directly. The regions created by eternal inflation lie far beyond the event horizons of each pocket. Light cannot travel between them. No signal can cross the expanding distance. This means the multiverse remains a theoretical framework. It can be supported indirectly if inflation's predictions match observations within our region, but it cannot be confirmed by seeing other regions. The observational boundary imposed by light and expansion prevents that. Even so, many scientists take the idea seriously because inflation solves several problems in cosmology. It explains the uniformity of the cosmic microwave background. It explains the flatness of space. It explains the origin of the small fluctuations that formed galaxies. And in many models, eternal inflation emerges as a natural consequence rather than an extra assumption. If the mathematics of inflation points to a multiverse, the idea becomes difficult to avoid. Some variations of the multiverse idea arise from other theoretical frameworks. In string theory, for example, the landscape of possible solutions to the equations describing the universe might contain many different configurations. Each configuration corresponds to a different possible set of physical conditions. Inflation could produce regions where different parts of this landscape become realized. Those regions could contain different laws of physics. This idea becomes speculative, but it shows how theoretical physics can lead to multiverse concepts from multiple directions, not just one. However, even when these ideas suggest different laws or different constants, the regions are still part of the same physical universe. They are not alternate realities separated by fundamental barriers. They are simply areas of space where inflation's end settled into different configurations. The boundaries between them are distances too vast to cross, not physical walls or transitions. This raises another point about boundaries in the multiverse picture. The boundaries between regions are not locations where conditions suddenly change. They are distances shaped by expansion. If you could travel far enough, the physical constants might change gradually or abruptly depending on the model. But you cannot physically travel that far. Expansion prevents it. The boundaries we talk about are observational rather than spatial. They represent the limits of what we can access, not the limits of what exists. Some versions of the multiverse picture include the possibility that inflation produced bubbles that collided with each other early in their formation. If two pockets formed close enough together before expansion separated them, their boundaries might have interacted. These collisions could leave subtle signatures in the cosmic microwave background. Scientists have searched for such signatures, but none have been confirmed. The absence of evidence doesn't rule out a multiverse. It simply limits the types of collisions that might have occurred within our observable region. Another multiverse concept arises from the idea of quantum fluctuations producing temporary forms of energy density. In this view, tiny regions might fluctuate into short-lived states resembling early inflation. These states collapse quickly, but in some rare cases, a fluctuation might last long enough to trigger a new inflationary region, creating a new pocket of space. This idea extends the multiverse concept further, suggesting that inflation can spontaneously produce new regions indefinitely. Again, this is highly speculative but arises naturally from the mathematics of quantum fields. When people imagine these pockets, they sometimes think of bubbles floating in a larger space. But the analogy can be misleading. These pockets are not objects drifting in a background. They are regions of space themselves. They don't sit inside anything. They are embedded in the same physical reality. There is no external volume. Space itself is divided into areas where inflation has ended and areas where inflation continues. The pockets don't move. The distances between them grow because expansion continues in the larger space. This growing separation leads to a universe with disconnected regions, each evolving independently. Some may experience similar developments, others may differ, but none interact. This scenario removes any sense of a universal center or edge. There is no point where the universe ends. There is only the extent of regions produced by inflation. Each pocket forms its own observable domain, with its own horizon. Some pockets might contain billions of galaxies, others might contain fewer. The variety depends on how inflation ended in each region. One of the challenges in discussing the multiverse is avoiding misunderstandings rooted in everyday experience. When people hear about different regions with different conditions, they often picture alternate dimensions or parallel universes in the science fiction sense. But in cosmology, the multiverse refers to regions of space-time created by inflation, not alternate planes of existence. They share the same physical reality but are separated by distances impossible to cross. They don't branch from decisions or events. They come from the way inflation behaves. Another challenge is that the word multiverse suggests something beyond normal science, but in cosmology the idea is a tool. It helps explain why our universe has the properties it does. It helps account for certain fine-tuned parameters. It helps model the consequences of inflation. Whether these regions truly exist, or whether they are artifacts of theoretical models remains an open question. But the idea emerges from attempts to build consistent theories, rather than from attempts to imagine dramatic scenarios. Sometimes people ask whether the multiverse makes boundaries meaningless. If there are many regions with different conditions, do boundaries have any significance? The answer is that boundaries still matter because they define what any observer can see. The fact that other regions might exist far beyond our horizon doesn't change the limits of our observable universe. The horizon remains the boundary of what light can reach. The multiverse simply adds the possibility that beyond that horizon, conditions may vary. It doesn't change the nature of the horizon itself. The multiverse possibility also raises questions about how typical our region is. If many regions exist with different conditions, ours might be one example among many. Some models suggest that only certain types of regions allow complex structures to form. In that case, observers naturally find themselves in regions where conditions support stability, star formation, and long-lived structures. Other regions might lack such stability. These differences arise not because the universe is designed that way, but because inflation produces a variety of conditions. Although the multiverse remains theoretical, it influences how scientists think about cosmic boundaries. If there are regions beyond our horizon with different properties, then the observable universe is only a local environment. Its boundaries are not universal boundaries. They apply only to observers in our region. Other regions have their own boundaries. Each region has its own horizon defined by the distance light has travelled since inflation ended there. These horizons overlap in the sense that each region has a sphere around it defined by light travel, but the boundaries never meet because the regions are too far apart. This perspective shifts how people think about edges. If the universe contains multiple inflation-born regions, then edges are not places where space ends. They are places where our view ends. What lies beyond may not be identical, but it is still space. It is still part of the same overall universe. There is no physical barrier dividing one region from another. The division is created by expansion's speed. Considering these possibilities leads to a broader understanding of why the universe might have boundaries that feel like edges, but are not edges in a structural sense. The multiverse picture doesn't claim that we can observe these regions. It doesn't predict new forms of direct evidence. Instead, it suggests that inflation's behavior might naturally produce a larger cosmic environment than we can see. It presents a universe filled with regions that form and evolve independently. It offers a way for edges to exist only as limits of vision rather than limits of existence. When most people imagine the universe, they picture something vast and open, stretching outward in all directions like an endless field. Others imagine it as a giant sphere, expanding into greater emptiness. Some picture a flat expanse with no edges, like a sheet that goes on forever. It's natural to use shapes we already understand because shape helps us make sense of distance, direction, and limits. But the universe doesn't behave like a shape we can hold in our hands. Its geometry is not something we can sketch easily. Understanding that geometry helps explain why the universe has boundaries that are not boundaries in any normal sense. It clarifies why the universe can have limits without having walls, and why distances can behave in ways that don't match everyday intuition. When scientists talk about the geometry of the universe, they don't mean shapes the way we use the word when describing physical objects. They mean the way space bends or doesn't bend on the larger scales. This bending is subtle. It affects how parallel lines behave, how triangles add up their angles, and how distances accumulate over vast stretches. Geometry in this sense describes the overall behaviour of space itself. If the universe curves inward, outward, or not at all, that curvature affects how the universe evolves. It affects what we can see, how light travels, and whether the universe is finite or infinite. One of the key insights from general relativity is that matter tells space how to curve. The geometry of the universe depends on how much matter and energy exist within it. If the amount is high enough, space can curve inward like the surface of a sphere. If the amount is too low, space can curve outward like a saddle. If the amount is just right, space can remain flat. This doesn't mean the universe is literally a sphere or a saddle. It means the rules for how distances behave match those shapes on a large scale. A curved universe can be finite but unbounded. That phrase sounds contradictory, but it has a precise meaning. Finite means the universe has a finite volume. Unbounded means you wouldn't encounter an edge. The classic analogy is the surface of a sphere. The surface is finite, but you can walk forever without hitting a wall. The surface curves back on itself. Space could behave like that in 3 dimensions. If it did, travelling far enough in one direction might bring you back to your starting point, though the distances involved would be immense. This type of geometry creates boundaries in how space behaves without creating physical borders. A universe with negative curvature behaves differently. It curves outward like a saddle. Such a universe is infinite. It stretches endlessly. Parallel lines diverge over distance. Triangles have angles that add to less than 180 degrees. The geometry affects how expansion works and how structures form. It also affects whether the universe will continue expanding forever or eventually slow. Negative curvature does not produce a finite volume, but it still shapes what we can observe because light behaves differently in such a space. A flat universe means the angles of triangles add to 180 degrees and parallel lines remain parallel. A flat universe can be infinite, or it can be finite if it has a special topology. Topology refers to how space connects to itself. A flat universe could be finite if it wraps around in certain ways. Imagine a video game world where walking off one side of the screen brings you back from the other. The space feels infinite, but it is actually a repeating loop. In 3 dimensions, space could have similar properties. It could be finite, but with a repeating structure that prevents edges. These possibilities show why geometry matters. The shape of space determines whether the universe is finite or infinite. It determines whether distances eventually loop or continue forever. But none of these shapes create walls. The geometry sets rules for movement and distance, not physical edges. This is why the universe can have boundaries in visibility without having boundaries in structure. The boundaries arise from how light travels, not from where space stops. The cosmic microwave background helps reveal the universe's geometry. The size of the temperature fluctuations seen in the background depends on how space bends. If space curves inward, the fluctuations would appear larger. If space curves outward, they would appear smaller. Measurements show that the fluctuations match a flat geometry extremely well. This suggests the universe is flat or very close to flat on large scales. A perfectly flat universe could be infinite, though it could also be finite if it wraps around. The data cannot yet distinguish between these possibilities. The near flatness of the universe is one of the successes of inflation. Inflation stretches any pre-existing curvature so much that space appears flat within observable regions. This flattening is similar to stretching a balloon until its surface looks flat to someone standing on it. Inflation can turn a curved space into one that appears flat locally. This supports the idea that the universe may be larger than what we observe. The flattening effect would dominate regardless of whether the universe is finite or infinite. Understanding geometry helps explain why the universe can have a horizon even if it is infinite. The horizon is not an edge of space, it is the limit of how far light has travelled since the universe became transparent. Light cannot travel infinite distances in finite time. The horizon marks the distance where light has had enough time to reach us. Even in an infinite universe, that distance remains finite. This finite horizon can make the universe appear bounded even if it extends endlessly. The boundary is an observational limit, not a structural one. Geometry also affects the fate of distant regions. In a flat universe with accelerating expansion, galaxies beyond a certain distance recede faster than light can travel. Light from those galaxies never reaches us. Those galaxies move beyond our event horizon. This horizon is shaped by expansion, not geometry alone. But geometry influences how expansion behaves and how the horizon evolves. In a curved universe, horizons would behave differently. In a universe with positive curvature, the geometry might slow expansion under certain conditions. In a universe with negative curvature, expansion might behave differently. The shape of space interacts with expansion and energy density to determine how horizons form. One of the interesting possibilities is that if the universe has a finite volume with a repeating topology, we might eventually see the same galaxy in multiple directions. This would happen if light travelled around space and reached us from different paths. Scientists search for patterns that might indicate such repetition. So far, no such patterns have been found. The universe may be too large, or the curvature may be too slight. But the possibility remains. If such repetitions were found, they would reveal the universe's shape directly. They would show that space loops in a specific way. Geometry also affects how structure forms. In a curved universe, gravity behaves slightly differently over large distances. The distribution of galaxies, clusters, and voids reflects the geometry. Observations of large-scale structure suggest a flat geometry, consistent with cosmic microwave background data. This agreement strengthens the idea that the universe is flat or nearly flat. But even in a flat universe, topology could create unusual connections. These connections would not create edges. They would simply shape how distances behave over extreme scales. The question of whether the universe is finite or infinite depends on geometry and topology. If space is flat and does not wrap, it could be infinite. If space wraps or has a complex topology, it could be finite. If space curves inward, it is finite. If it curves outward, it is infinite. Current data cannot determine the full topology because the region we observe is limited. The universe could be finite and large enough that repeated patterns lie far beyond our horizon, or it could be infinite. Geometry gives rules for possibilities, but observation gives limits for what we can know. Regardless of whether the universe is finite or infinite, geometry creates boundaries based on how light moves. In a positively curved universe, light travelling in different directions might converge. In a negatively curved universe, light diverges. In a flat universe, it behaves predictably. These behaviours affect what we see when we observe distant regions. They affect how large structures appear. They influence how the cosmic microwave background maps across the sky. Geometry becomes a quiet background rule shaping every observation. The shape of space also affects how time evolves. In relativity, space and time form a single spacetime. The curvature of space affects the curvature of time. This influence determines how quickly clocks tick in different regions. It affects how gravitational wells form and how strong they become. It shapes the paths objects follow. Geometry doesn't only create boundaries in space, it influences the boundaries in time, in communication, and in causality. Causality refers to what can influence what. Geometry affects whether two regions can communicate. In a curved universe, certain paths might be shorter or longer than expected. Expansion complicates this further by stretching distances. Combining geometry with expansion creates a dynamic set of boundaries. These boundaries change over time. They don't remain static. The observable universe grows or shrinks in terms of what it contains depending on expansion. Geometry determines how that change unfolds. One subtle point about geometry is that it influences how we interpret distances. In curved space, straight lines may not behave as expected. The shortest path between 2 points might not be a straight line in the everyday sense. This affects how light travels. Light always follows the shortest path possible through space-time. If space-time curves, light bends. This bending helps explain gravitational lensing. A massive object curves space-time. Light passing near it bends. This effect can magnify distant galaxies, revealing structures that would otherwise remain hidden. Geometry allows us to see farther in some cases because gravity reshapes the paths of light. Gravitational lensing also reveals the distribution of dark matter. Dark matter does not emit light, but its gravitational influence bends light. By observing how galaxies distort in cluster images, scientists map dark matter. This mapping depends entirely on the geometry of space. Curvature reveals invisible structures. It helps scientists trace how mass is distributed. Geometry becomes a tool for uncovering otherwise hidden components of the universe. As we consider the geometry of the universe on the larger scales, one of the most important insights is that the observable universe has limits because of geometry, not because of confinement. A flat universe without edges can still have a horizon. A curved universe without walls can still limit what we see. These limits don't reflect boundaries in what exists, they reflect boundaries in what light can reveal. This distinction is important. It means that even if the universe is finite, we might not reach its larger scale. Horizons could occur long before any spatial boundary. If the universe is infinite, horizons could occur because the universe expands faster than light can travel. In both cases, the limits arise from geometry combined with expansion. They aren't edges of space, they are edges of visibility. Another important insight is that the universe's geometry might not be the same everywhere. Inflation predicts that each pocket formed from inflation could have its own geometry. One region might be nearly flat, another region might curve slightly, another might have a different topology. These variations would not violate physics. They would simply reflect how inflation ended in different regions. Each region would have its own large-scale shape. This possibility ties back to the idea that the universe extends far beyond our observable region. Considering all of this leads to a broader understanding. The universe does not require edges to have limits. Geometry alone can create the conditions where certain distances remain unreachable. Combined with expansion, geometry shapes the horizons that define our view. It also shapes the fate of light and the structure of cosmic evolution. When people think about the future of the universe, the imagination often jumps to ideas that feel dramatic or cinematic. Maybe everything collapses back inward. Maybe stars ignite in spectacular finales. Maybe civilizations travel endlessly into distant galaxies. But the real future that physics points toward is quieter, slower, and shaped by a simple but relentless process: expansion. The same expansion that stretched space in the early universe, separated galaxies across cosmic distances, and pushed some regions permanently out of reach will continue far into the future. As expansion persists, the universe's boundaries will shift in a way unlike anything we experience on human timescales. It won't end with an explosion or a collapse. It will fade, it will stretch, and gradually it will cool into a state where structure becomes rare, light grows faint, and time smooths everything toward a quiet equilibrium. The direction the universe is heading becomes clearer when you understand the forces shaping its long-term evolution. One of those forces is dark energy, the mysterious component of the universe that causes expansion to accelerate. Dark energy doesn't behave like matter or radiation. It doesn't thin out as the universe grows. Instead, it remains nearly constant. As more space forms, more dark energy appears with it. This property causes expansion to speed up rather than slow down. Because of dark energy, the distances between galaxies increase faster over time. This acceleration determines much of the universe's distant future. To understand that future, it helps to picture what happens within the next tens of billions of years. Right now, galaxies outside our local region are drifting away from us. Light from those galaxies still reaches Earth because it was emitted billions of years ago. But as expansion accelerates, many galaxies will eventually move beyond our event horizon. The event horizon marks the distance beyond which light emitted today can never reach us. Galaxies that are now visible will gradually cross that limit. When they do, their future light will never arrive. We will continue to see their past light until the final photons reach us. Then, slowly, they fade from view. This fading is not abrupt. It takes billions of years. A galaxy moves toward the horizon at a pace dictated by expansion. As the space between us grows, the galaxy's light stretches more and more. Redshift increases. The wavelengths shift into infrared, then microwave, then radio. The brightness drops accordingly. The galaxy becomes harder to detect. Eventually it disappears from any possible observation. It still exists, It continues forming stars, evolving and interacting with nearby galaxies in its own region. But from our perspective, it becomes unreachable. As expansion accelerates further, more galaxies cross the horizon. The observable universe shrinks in terms of what it contains. Even though the radius grows slightly with time because more past light arrives from just inside the limit, the number of visible galaxies decreases. Within trillions of years, only the galaxies gravitationally bound to the local group will remain visible. All others will have slipped beyond reach. The sky becomes emptier in the deep cosmic sense. Darkness increases not because stars go out, but because distance grows beyond communication. The local group of galaxies, including the Milky Way and Andromeda, remains bound because gravity overcomes expansion on small scales. Those galaxies will merge into one large galaxy over time. Within tens or hundreds of billions of years, this merged galaxy will contain all the stars still reachable to any observer living within it. Everything else will lie outside the horizon. The broader universe continues expanding, but the visible portion becomes a quiet island surrounded by unreachable space. Stars themselves will continue shining for a long time. The longest-lived stars are small, cool red dwarfs. They burn slowly and efficiently. Some will last for trillions of years. These stars will provide light long after larger stars have expired. But as time passes, fewer new stars form. Star formation requires gas, and that gas becomes locked in existing stars or expelled through stellar processes. Over time, the supply diminishes. Star formation slows and eventually stops. The universe enters a phase where stars age without being replaced. Large stars burn out quickly. Medium stars like the Sun live for billions of years before becoming white dwarfs. Smaller stars last longer, but eventually exhaust their nuclear fuel. After the primary phase of the universe's history ends, the cosmos moves into an era dominated by remnants. White dwarfs, neutron stars, black holes, and drifting planets. These objects remain for incredibly long periods, slowly cooling and fading. White dwarfs gradually radiate away their heat. Given enough time, they cool to the point where they emit almost no light. They become cold, faint objects sometimes called black dwarfs. These remnants contribute little illumination. Neutron stars also cool, though they remain dense and compact. Black holes persist, slowly evaporating over unimaginable timescales. As star formation ceases and existing stars burn out, the universe grows darker. The process is slow, it takes trillions of years. But expansion accelerates the sense of isolation. Even though remnants persist for enormous periods, the observable environment shrinks. Only a handful of remnants remain within view. The universe seems quiet, almost static from the perspective of any observer who might exist far in the future. Expansion doesn't stop when the stars fade. Dark energy continues pushing space apart. Distances double, then double again. The rate of doubling depends on the behavior of dark energy. If dark energy remains constant, expansion continues exponentially. If dark energy changes, expansion could behave differently, but current evidence suggests that dark energy will remain at or near its current density. In that scenario, the universe expands at an accelerating rate indefinitely. In this far future, galaxies outside the local group are not merely distant, they are unreachable. Even if an observer attempted to send a signal, that signal would never arrive. The space between regions grows too fast. The expansion rate outpaces any communication. This isolation isn't due to voids or emptiness, it's due to geometry and expansion. Over time, this isolation becomes complete. The universe becomes a set of separated regions, each containing only the material bound within it. The dwindling of visible matter marks a shift in cosmic conditions. As stars fade and remnants cool, the remaining structures become dominated by gravitational interactions. Black holes may merge or capture nearby objects. Mass continues to move under gravity, but the environment grows quieter. Even collisions between remnants become rare as distances increase. black holes remain among the most enduring objects. They persist for extraordinarily long times through a process called Hawking radiation. This radiation causes black holes to lose mass extremely slowly. A stellar mass black hole might take 1067 years to evaporate. Larger black holes might take even longer. During these epochs, black holes gradually shrink. Eventually they evaporate entirely. They release their remaining mass as bursts of radiation. After these events, only a diffuse cold universe remains. As the universe enters these late phases, the average temperature continues to drop. The cosmic microwave background cools further as expansion stretches its light. Today it sits at about 2.7 degrees above absolute zero. In the distant future, it will cool to thousandths of a degree, then millionths, then smaller fractions still. Eventually, the cosmic microwave background becomes so faint that it no longer provides measurable heat. The universe cools to near equilibrium. This slow decline defines what is sometimes called heat death. Heat death doesn't mean everything stops. It means the universe reaches a state where temperature differences no longer drive processes. Without temperature gradients, energy cannot flow in ways that sustain structure or activity. Everything drifts toward the same cold, diffuse state. Motion persists, but transitions become rare. Systems move toward a uniform distribution of energy. This equilibrium represents the long-term outcome of expansion. It reflects the idea that over time, usable energy becomes less available. Stars once provided enormous amounts of usable energy. Remnants provide less. Eventually, most energy becomes locked in low-grade radiation or distant particles. Even as the universe cools, expansion continues shaping its structure. If dark energy remains constant, expansion accelerates indefinitely. Galaxies recede from one another faster and faster. Remnants drift apart. Any local region becomes increasingly isolated. Large-scale structure becomes irrelevant because distances grow too vast for gravitational influence to remain effective over long ranges. At extremely distant times, far beyond the lifespan of black holes, the universe consists primarily of photons, neutrinos, and a thin mist of particles. These particles continue drifting in an expanding space. They carry tiny amounts of energy. They interact rarely. Expansion stretches their wavelengths further, reducing their energy even more. After unimaginable lengths of time, the universe becomes dominated by low-energy radiation, drifting freely across a vast, expanding space. This picture might seem bleak, but it reflects how physical laws behave over extreme timescales. The universe doesn't end in sudden destruction. It simply cools and fades. Processes that once shaped galaxies slow. Stars that once illuminated the universe no longer shine. Remnants that once formed the backbone of structure gradually disappear. Expansion acts as the slow, guiding force behind these changes. This long-term future also highlights something important. The boundaries of the universe change with time. Today, the horizon marks the limits of what light can reach us. As expansion accelerates, the horizon shrinks in what it contains. More galaxies cross the event horizon. More regions disappear from view. In the far future, only the remnants within the merged local structure remain visible. Horizons shift as the universe evolves. They reflect the limits of information, not the limits of space. Even as the observable universe contracts in what it contains, the actual universe does not shrink. Expansion continues making the universe larger. Space grows without limit. The visible part becomes a vanishing fraction of the whole. From a future perspective, observers might see only a small region of the cosmos, unaware of the vast expanse beyond. Their knowledge would depend entirely on the remnants around them. The evidence of expansion would be faint. The cosmic microwave background would be nearly impossible to detect. The early universe's details would be lost to obscured signals. Understanding the larger cosmos would become extraordinarily difficult. These limitations show why our current era is important for scientific knowledge. Today, the universe contains enough accessible information to understand its history. We can detect the cosmic microwave background, we can observe distant galaxies, we can study large-scale structure. In the future, much of this evidence disappears beyond reach. The structure becomes difficult to interpret. The universe grows dark. Knowledge becomes constrained by what remains visible. The long-term fate described here assumes that dark energy remains constant. If dark energy changes, the future could shift. Some theoretical models allow for possibilities where expansion slows or changes behavior, but current observations strongly support continued acceleration. If that continues, expansion remains the dominant force shaping the future. As the universe moves deeper into this distant era, the ideas of edges and boundaries take on new meaning. The observable region shrinks. The horizon defines what remains visible. But the universe itself continues expanding. No structural edges appear. Space stretches indefinitely. The future becomes defined by isolation, cooling, and gradual movement toward equilibrium. These changes invite another perspective on the idea of the universe's limits. If expansion pushes everything apart and cooling spreads evenly, then the future's boundaries are shaped not only by light's reach, but by the fading of energy itself. The universe becomes a place where signals weaken over time, not because of interference or distance alone, but because energy gradually spreads into increasingly thin forms. When you spend a long time wandering through the story of the universe, moving from the earliest moments to the farthest edges, it becomes clear that the boundaries we imagine are almost never the boundaries that exist. The edges we picture when we think about the cosmos aren't walls, endings, or cliffs hidden behind distant galaxies. They are limits created by time, by the speed of light, by expansion, and by the behavior of energy across enormous scales. As you drift back from the idea of an edge and return toward a calmer perspective, the universe begins to look less like a place that ends somewhere, and more like a place where your view naturally fades because the light grows too thin, the distances grow too large, and the signals grow too stretched to reach you. It's helpful to take a quiet step back and think about how many different kinds of boundaries you've traced on this journey. There's the limit of how far you can see today, marked by the observable universe. That limit depends on the distance light has travelled since the universe became transparent. There's also the event horizon, which marks the distance beyond which light emitted now will never reach you because expansion outpaces it. There's the reach of Redshift, revealing how light thins and cools as it crosses growing space. There's the limit set by the cosmic microwave background, which forms the earliest visible surface in time because earlier eras were too hot and dense for photons to travel freely. These boundaries are not slices of the universe, they are slices of information. Drifting across these ideas brings you toward an understanding that the edge you thought you were seeking isn't something the universe hides, it's something your perspective creates. The universe doesn't organize itself around what you can see, it simply evolves according to physical laws. The boundaries form from the interplay of those laws with your position in time and space. This perspective leaves you with a quieter appreciation for how the universe actually behaves. Instead of imagining an outer wall where everything stops, you begin to recognize a softer, more layered gradient. One that gradually transitions from what is visible to what is beyond reach, not because anything disappears, but because light cannot cross the distances quickly enough to bring you the information. As you return from the far regions to something more familiar, it can be grounding to revisit the way expansion shapes everything. Expansion isn't a force pushing galaxies apart. It is the gradual stretching of space itself. That stretching determines how far you can see, how fast galaxies appear to recede, and how redshift grows as light travels for billions of years. When expansion accelerates because of dark energy, the horizon tightens in what it contains, not in size, but in what can remain visible. It is this long-term behavior that creates a future where galaxies slip away, signals fade, and the universe becomes a quieter place. Thinking about this transition raises another idea that has accompanied you throughout this entire exploration. The universe changes not just in space, but in time. The boundaries are dynamic. The edges aren't fixed. They move, they shift, they respond to expansion. In the early universe, when space was small and compact, the boundaries that exist today had no meaning. As the universe grew, light gradually filled more space. The observable region expanded in what it contained. Over longer scales, as acceleration dominates, that region contracts in what remains visible. Boundaries evolve with cosmic history. This movement shows something important about edges. They are tied to time as much as to distance. They are markers of what has had enough time to reach you and what hasn't. They depend on when light began its journey and how space behaved during that journey. This connection between time and visibility appears again and again, from the cosmic microwave background, which shows the moment when the universe became transparent, to the deep red-shifted light of distant galaxies, to the fading signals from the earlier stars. Everything reveals information about how time and distance combine to shape what can be observed. As you bring these ideas closer together, you might notice that the universe gives you only a partial view of itself, not because something is hiding, but because the laws of nature don't allow unlimited access. No matter how powerful your instruments become, no matter how far science advances, some regions remain permanently beyond communication. They were pushed too far away by inflation or later expansion. Their light will never arrive. The universe is large enough that even the most ambitious curiosity has natural boundaries. But the presence of these boundaries isn't a limitation in the frustrating sense. They are clues. They reveal the structure of space-time. They show how inflation behaved. They indicate how expansion evolves. They help explain why the universe appears flat, homogeneous, and full of structures at particular scales. If the universe had no boundaries at all, you wouldn't be able to infer much from what you can see. The boundaries shape the clues. They reveal the underlying geometry. They show the distribution of matter and energy. They confirm predictions made by theory. Boundaries are part of what allows the story of the universe to be decoded. You've also travelled through the idea that the universe might contain more regions than the one you can see. In models of eternal inflation, the universe becomes a framework for many regions where inflation ended under different conditions. Some of these regions might resemble ours. Others might have differences in the distribution of matter or the details of early fluctuations. These regions aren't alternate realities in the dramatic sense. They are merely distant parts of a universe that expanded too rapidly for them to interact with each other. They share the same existence, governed by the same physics, but separated by distances that expansion continues to widen. The possibility of multiple regions helps demonstrate why the edge of the observable universe is not an outer limit for everything that exists. It is just the limit of information available to you. This is not only a physical fact, it is a conceptual anchor. It changes how you imagine the structure of the cosmos. Instead of thinking of the observable sphere as a container, you begin to see it as a window framed not by borders in reality, but by borders in access. As the journey starts returning toward the center of your awareness, you can revisit the geometry that shapes your window. The universe appears nearly flat, meaning space doesn't curve significantly across the observable region. This flatness aligns with inflation's predictions. It also suggests that space might extend much farther than the part you can see. It could be infinite, or it could be finite but extraordinarily large. Geometry doesn't need edges to limit motion. It simply sets the rules under which distances accumulate. Light follows those rules, galaxies follow those rules, the horizon follows those rules. What you perceive as structure emerges from the geometry of space-time more than from any physical outline. Reflecting on this leads naturally to the idea of what happens far in the future. Expansion doesn't stop. It keeps stretching space. Galaxies drift apart. More regions move beyond the event horizon. light from distant structures becomes too stretched to detect. The universe grows cold as stars fade and remnants persist quietly. The cosmic microwave background cools to a faint, almost impossible to detect whisper. Eventually, black holes evaporate. Even these robust structures fade into low-energy radiation over extremely long timescales. This long-term picture shows how the boundaries of visibility continue to shrink. In the distant future, any observer would find themselves in a small island of light surrounded by vast, unreachable darkness. Their knowledge of the universe would be shaped entirely by what remains within their horizon. The clues available today, distant galaxies, cosmic background radiation, large-scale structure, would not exist for them. They would see a quieter universe, a simpler universe, one where expansion has erased much of the accessible history. The contrast between their perspective and ours offers another insight. The universe is most knowable at certain points in its timeline. Today is one of those points. The cosmic microwave background is detectable. Distant galaxies are visible. Expansion's history can be traced. But the moment when all of this becomes inaccessible is part of the same story. The universe's boundaries are not fixed. They change with time. They depend on the behavior of energy and expansion. They arise from natural processes that unfold whether anyone observes them or not. Moving through these ideas brings you back toward a space where you can see how the entire journey connects. Beginning from the earliest light, traveling through the nature of horizons, exploring the effects of expansion, visiting the idea of multiple regions produced by inflation, following the geometry of spacetime, and stepping into the future of heat. Death and isolation creates a continuous picture. Each part supports the next. Each idea builds on the last. The universe becomes something comprehensible, not because it shares human scale, but because the laws that govern it remain consistent across all scales. As you drift back from the conceptual rim of what the universe allows you to see, the most striking realization is that science doesn't need edges to describe limits. It doesn't need walls to describe boundaries. It simply follows the behavior of light, space, and time. Light reveals information. Expansion shapes pathways. Geometry determines how those pathways behave. All the boundaries emerge from these interactions. They aren't imposed. They arise naturally. You also see that moving toward the edge, whether toward the horizon of the observable universe or toward the distant idea of the cosmic event horizon, doesn't bring you closer to an ending. It brings you closer to an understanding that endings in the cosmic sense don't occur in space. They occur in visibility. They occur in communication. They occur in the ability of information to travel. When the universe expands fast enough, the edges form not because anything stops, but because the signals cannot keep up. This understanding makes it possible to return to a quieter sense of perspective. Instead of picturing the universe as something that has a frontier waiting to be reached, you can picture it as something that reveals what it can based on fundamental limits. The cosmic story isn't a journey toward a wall, it's a journey toward a deeper acceptance of how information moves through space-time. As you settle back from the edges of what the universe reveals, everything becomes calmer. The galaxies resume their distant glow. The cosmic microwave background forms its quiet curtain of faint radiation. Light continues drifting from star to star. Expansion remains slow enough in your daily experience that it becomes background rather than focus. The universe continues stretching, but at human scales its changes are gentle, almost unnoticeable. Everything large and distant continues its motions without requiring urgency or immediacy in understanding. This shift back toward the familiar doesn't undo the vastness you've travelled through. It simply places it in a context where the mind can rest. You've seen that the universe is not structured around clear borders. You've seen that the idea of an edge is shaped by visibility more than by existence. You've seen that the future holds a slow change toward cooling and fading rather than sudden transitions. You've seen that the universe grows more isolated as expansion accelerates, but that it continues operating according to the same rules that shaped its earliest moments. Returning from that scale brings you to a moment where the universe feels more approachable. The sky above you does not show the limits you explored, but it holds the same physical truths. Every visible star, every faint galaxy, every trace of background radiation operates within the framework you've traced. The cosmos contains immense distances, long histories, and evolving boundaries. But from your perspective, it remains a single continuous environment where light arrives steadily and calmly from across the great stretches of space. And so you drift back from the rim of what the universe can reveal, carrying with you the quiet understanding that the edge is not a place but a limit in what signals have had time to reach. What lies beyond those limits continues existing whether anyone sees it or not. The universe extends in all directions, governed by consistent laws. Horizons shift, distances grow, structures evolve, the cosmos continues unfolding in its own measured way.